Buenos días. Profesor Felipe, ¿está ahí?
Hola, buenos días.
Hola, ¿cómo vamos?
Bien, ¿y
Muchísimo
ustedes?
Buenos
gusto.
días.
¿Qué tal, Felipe? Finalmente nos vemos.
Sí, finalmente,
Bueno, Felipe es de Bogotá, imagínense
sí, de
ustedes,
Bogotá. Sí,
Sí, sí, sí, de la casa, aquí
de
en
la
el...
casa. Está jugando de local de forma virtual, Felipe.
exacto. Hace rato no voy, tengo que ir pronto otra vez.
¿Sí?
Con
¿Hace
la
cuánto?
pandemia ya difícil, sí. Desde antes de la pandemia,
Ya.
Ish.
Caramba.
de 4 años, sí.
Sí.
Ya está picando volver.
Ya está picando.
Sí, ya toca pronto.
Ah,
Yo también debido a la pandemia no pude ir, pero hace 2 semanas regresé.
Ok,
Ah,
qué bien.
que
Sí.
hay que pasarse por la Candelaria, ¿no? Un poquito.
¿La
Hombre,
Candelaria
Felipe,
qué es, güey?
una parte del centro de Bogotá que es bien bonita,
Ah,
la parte histórica.
ok.
Sí.
Como de San Antonio de Cali.
Como
Ya, ya,
así,
ya, ya, ya. Buena analogía.
Dubán, ese fondo que tienes tú es que de esa biblioteca o
es una biblioteca en Francia,
en Francia.
sí.
Chévere,
Una
muy
parte
chévere.
de la Biblioteca Nacional de Francia. Me encanta. Felipe, ¿eres de la Nacional? ¿De la Nacional?
De los Andes, dice el
De
De
los
pregrado.
los
Andes.
Andes.
Sí,
Ah, ok, ok.
sí. ¿Ustedes son de Univalle todos o?
Sí.
Sí, todos egresados de la universidad.
Qué chévere, qué bien.
Es decir, a Brian y a Jessica los aguanté como por 5 años. Fue terrible.
¿Se
Ay,
conocieron
bendito.
ustedes con César? Cuando
Con César
estaban al
Ceballos.
mismo tiempo. César Ceballos, sí.
Después lo conocí yo, pero cuando yo
Pues
entré, yo creo que él ya había salido cuando entramos nosotros.
sí.
Ya se
Ok,
había grabado.
ok.
Ya sabemos, ¿no? Felipe trabaja en el campo de la combinatoria. Es
Sí,
verdad,
a
¿no?
César lo conozco desde hace rato. Sí.
Sí.
Sí, sí.
Pues imagínense que le escribí a Claudia Gareto, pues es una colega, y me dijo, Duan, tienes que invitar a Felipe Rincón. Y para mí fue increíble. Yo, ¿cómo así? Hay un bogotano en la Universidad de Bath. Y mira,
En Queen Mary, en la
En Queen
Universidad.
en
Mary.
Queen Mary.
Sí.
Mm,
En Queen Mary.
Claudia acaba de llegar a Queen Mary hace como 6 meses.
Ok, ok.
Sí. Sí, Claudia, sí, la conozco hace poco, pero me cae muy bien Claudia, sí, chévere.
Es súper amable, ¿no? Claudia es increíble.
Mm, mm. Y hace un montón de cosas en el departamento, siempre está ahí pendiente de todo.
Parece, parece italiana, ¿no? Activa.
Pero también muy latina, ¿no? Como que le gusta harto estar en conexión con los latinos y habla español
Sí,
perfecto, creo. Nunca he hablado español con ella, pero creo que habla español muy bien.
sí. Es que su pareja es músico, es cubano, algo como esto.
Ya entiendo todo.
seguramente
Sí,
por eso.
Ya tiene
el
sentido.
amor a la salsa. Jessica sabe, es una experta en el área también. Bueno, yo voy a mutearme y
Ujú. Yo creo que ya podemos comenzar, si les parece a todos.
Sí,
Entonces, Felipe, si quieres, puedes compartir la pantalla mientras
listo,
hacemos
déjame.
tu presentación, solo
eh,
para verificar que esté todo en orden.
ahí ya listo.
Ok, listo. Vamos, Jessica. Jessica.
One moment, please.
Ah, ok.
So, yo voy a empezar el discurso en español y Brian lo va a decir en inglés, ¿ok? Entonces, muy buenos días. Abrimos este último día de conferencia con esta increíble charla titulada Algebraic Functions for Tropical Geometry, a cargo del profesor Felipe Rincón. Es realmente un placer tenerlo con nosotros en este evento y personalmente encuentro muy interesante el tema que nos va a hablar hoy. Déjenme contarles un poco acerca de la trayectoria del profesor Rincón.
Good morning. We opened this last day of conferences with this amazing talk entitled Algebraic Foundations for Tropical Geometry by Professor Felipe Rincón. It is really a pleasure to have you with us at this event, and I personally find the topic that you are going to talk about today very interesting. Let me tell you a little about the trajectory of Professor Rincón.
Obtuvo su título summa cum laude en matemáticas en la Universidad de los Andes, donde también realizó su maestría bajo la dirección del profesor Federico Ardila. Posteriormente, obtuvo su doctorado en la Universidad de Berkeley bajo la dirección de los profesores Bernd Sturmfranz y Olga Holst. A pesar de ser tan joven, el profesor Rincón posee un amplio historial académico y científico. Posee una inconsiderable cantidad de artículos publicados en revistas de alto impacto internacional y ha recibido varios reconocimientos entre los que podemos destacar el Premio Nacional de Ciencias Exactas, Físicas y Naturales, Fundación Alejandro Ángel Escobar en 2015. Desde muy joven mostró talento para las matemáticas, obteniendo excelentes resultados en Olimpiadas de Matemática.
He obtained his bachelor summa cum laude degree in mathematics at the Universidad de los Andes, where also he studied his master's degree under the direction of Professor Federico Ardila. Then he obtained his PhD from UC Berkeley under the direction of Professor Bernd Sturmfeld and Olga Holst. Despite being so young, Professor Rincón has an extensive academic and scientific record, has a considerable number of articles published in journals of high international impact, and has received several awards, among which can highlight the Premio Nacional en Ciencias Exactas, Físicas y Naturales, Alejandro Ángel Escobar Foundation in 2015. From a very young age, he showed a talent for mathematics, obtaining excellent results in Mathematics Olympics.
Actualmente es profesor de álgebra en Queen's Mary University of London y enfoca su investigación en aspectos combinatorios de objetos geométricos y algebraicos. Es momento de hablar de geometría tropical, profesor.
He is currently a senior professor of algebra at Queen Mary University of London and focuses his research on combinatorial aspects of geometric and algebraic objects. It is time for tropical geometry.
Bueno, muchas gracias por la introducción y muchas gracias al comité organizador y al comité científico por la invitación. Muy chévere ver este tipo de eventos que muestra cómo ha crecido la matemática en Colombia y en Latinoamérica en general. Esperemos que no sea el último, obviamente. And now let me switch to English. The plan for my talk is to tell you a bit about algebraic foundations for tropical geometry. So this is something I've been thinking about for the last 7 years or something like that. And I'm not going to assume that you know anything about tropical geometry. So the first part of my talk is just going to give you an introduction from the very basics, because I know the audience here is quite diverse. So from the very basics, I'm going to start telling you about introducing you to tropical geometry, and then by maybe the last third of the talk, I'll actually tell you something about my research on trying to develop algebraic foundations. Okay. So let's start with the simplest thing I can tell you about, which is tropical arithmetic. What is tropical arithmetic? Well, the tropical semi-ring is going to be the real numbers together with one more element, infinity, plus infinity. So it's an element that is larger than any other real number. And it's going to have two operations. It's tropical addition, which is going to be taking the minimum of the two elements, and tropical multiplication, which is going to be taking the sum of the two elements. Okay, so in the tropical semi-ring, for example, 3 plus 5 is 3, because the minimum between 3 and 5 is 3. And the multiplication of 4 and 7, the product of 4 and 7 is going to be 11, because 4 plus 7 is 11. Right? So remember, addition is minimum, multiplication is addition. And the reason we put infinity as an element there is because we want to have an additive identity. So infinity plus any number is going to be that number. The minimum between infinity and a is always equal to a. And now the multiplicative identity is going to be 0. 0 times any other number is that other number. Okay, so keep this in mind because it's easy to get confused with this. When I write infinity, I mean the additive identity, and when I write 0, I mean the multiplicative identity. Okay, so this algebraic structure turns out to be a semi-field. So in the sense that it's almost a field, it satisfies all the axioms of a field. For example, distributivity holds. If you take A times B plus C, that's going to be the same as A times B plus A times C. And the only thing that doesn't work is that there are no additive inverses anymore. So it's almost a field, except that there are no additive inverses. You cannot solve an equation like this. 2 plus something is never going to give you 5, because the minimum between 2 and anything else is going to be at most 2. It can be less than 2, but it cannot be more than 2. It cannot be 5. So it's a semi-field, and it's an idempotent semi-field. That means that addition is idempotent. So whenever you take an element and you add it to itself, you just get that element back. Okay, it's an idempotent semi-field. And I'm going to be talking, I want to do algebraic geometry over the tropical semi-ring. I want to do tropical algebraic geometry. So I'm going to be talking about polynomials. And I'm going to denote by this R bar. So tropical numbers adjoined with the variables x1 up to xn. That's going to be, now it's a semi-ring of tropical polynomials, meaning that there is no, it's almost a ring, but there is no additive inverses. So tropical polynomials are just like polynomials, but the operations are tropical operations. And let's just start with very simple examples. Here's a univariate polynomial in one variable x of degree 2, x squared plus 1x plus 4. And remember that 1 is not the multiplicative identity, so it really matters that I say here 1 times x, 1 times x is really not the same as x. X would be 0 times x, because 0 is the multiplicative identity, but 1 times x is something else. And when I say x squared, I really mean x times x, tropical times x. So x plus x, which is 2x, right? If we try to draw the graph of this polynomial, well, it's going to be the minimum of 3 things. Minimum because we have these tropical pluses here. The minimum between 2x is the first term. If we use classical notation, this is just 2x. This is x plus 1. The term in the middle is x plus 1, and the constant term is 4. So we get the minimum between these 3 affine linear functions that I have here in this graph, and then, well, the minimum is attained at is the orange thing I drew. Okay, that would be the graph of a tropical polynomial, and you can see that it's going to be some kind of piecewise linear thing, right? So something that is not linear, but it's linear piece by pieces. In 3 pieces, it's linear. And well, if you play a little bit with the polynomial, you can see that it actually factors as a product of 2 linear polynomials, of 2 polynomials of degree 1, x plus 1 and x plus 3. Okay, you can. If you expand this out using the distributivity, you'll see that you get back the polynomial you started with. So in some sense, you want to think of 1 and 3 as being the tropical roots of the polynomial, because you can factor it using those linear polynomials. And it's nice that you can actually see the 1 and the 3 in the graph, as these are the places where the graph bends, right? This is a piecewise linear function, and it breaks in some points, and those points are exactly when x is equal to 1 and when x is equal to 3, which turn out to be the things that you need to put here to factor the polynomial into linear factors. That's not always going to be the case, but almost in the following sense. So here's another example: x squared plus 3x plus 4. So now you have the minimum again of 3 linear functions. The first one is 2x. The second one is now x plus 3. So it's the same one we had before, but maybe shifted 2 units upwards. And then 4, which is the same as we had before. And now you see that the term in the middle doesn't really play a role, because it's like the minimum is never attained at this function in the middle, at this 3 plus x. And now in this case, you cannot factor the polynomial literally as a product of 2 linear factors, but as functions. So you can find another tropical polynomial that is the same as this one for all values of x, even though when you expand it out, you don't get exactly the same coefficients. You get so if you take x plus 2 times x plus 2, you expand it out, you get a 2x in the middle instead of 3x, but the graph of the 2 polynomials is the same. So yeah, you cannot factor the original polynomial. Oops, you cannot factor the original polynomial as a sum of, as a product of linear factors, but as functions you can. Okay, and this is the, let me just state this so that we start getting a sense of what kind of things we care about in tropical algebraic geometry. There's some fundamental theorem of algebra, tropical fundamental theorem of algebra, which tells you that whenever you have a univariate polynomial, tropical polynomial of degree d, you can always factor it as a product of linear terms, and then with some multiplicities, so that the multiplicities add up to the degree of the polynomial. And yeah, and the roots, so the constant terms in the linear factors that you have are exactly the places where the graph bends, where the graph of your polynomial actually breaks. Yeah. And this is factorization as functions. So it's really not an equality of polynomials, but an equality of functions from the real numbers to the real numbers, as we saw before. And this is really an exercise. So if you have some time later and you're curious about these things, you should try to convince yourself that this is true. We don't need a Gauss to prove this fundamental theorem of algebra in the tropical world. It's really a much simpler statement. It's just an exercise to realize that whenever you have a minimum of these linear functions, you can factor it as a product of linear forms. So in that sense, tropical geometry kind of simplifies a lot the classical algebra that we have. Now let me go to higher number of variables. So suppose now that we have a polynomial in n variables, not one variable anymore, or a tropical polynomial in n variables, and we want to define what the zero set of this tropical polynomial is in such a way that it generalizes the concept of roots that we had before. Well, a tropical polynomial is always going to be the minimum of a bunch of terms, because addition is minimum, and these terms are going to be affine linear functions. They're going to be, because multiplication is addition, then what you get is just really the minimum of a bunch of linear functions. And we want to define the tropical zero set, or the tropical hypersurface defined by that polynomial, to be the places, the values of A in n-dimensional space, tropical n-dimensional space, where the minimum at all those terms is attained by at least of those terms, right? So that's exactly saying that that's one place where the graph bends. It's saying that we're sitting at a point where two of these terms actually attain the same minimum when you draw the graph. That's another way of saying this would be is the places where the graph of the polynomial bends. Okay, so here's a picture I drew so that this is completely clear for all of us, hopefully. If you take a very simple polynomial, linear polynomial in two variables, x and y, 2x plus 1y plus 3, well, this is the minimum of three linear functions, affine linear functions, x plus 2, y plus 1, and 3. And if you draw the graph in three-dimensional space, you can imagine it as the picture I have here on the left. It's like a tent on one part. The minimum is x plus 2, and another one is y plus 1, and over here it's the constant 3. And those three linear functions meet at some points, and that's exactly the values of x and y, where the minimum is attained by at least two of the three terms. And that happens exactly on top of the set that I have drawn here on the right, the orange set. So yeah, hopefully that's clear. So it's like you would say that the tropical hypersurface defined by this linear polynomial, or the tropical line, because this is a linear polynomial, this you should think of a line in two-dimensional space, a line in affine two-dimensional space, a tropical line. It's going to look like this. It's going to have some vertex, and then out of that vertex, there's a vertical ray coming out, a horizontal ray, and then a diagonal ray as well. That's a picture of a tropical line. If maybe several of you have seen these kinds of pictures before. Here I have more examples of, now this is a quadratic in the plane, because it's the zero set of a quadratic polynomial, 1xy plus 2x plus 1y plus 3. Now you have four affine linear functions that make the graph of the polynomial, and they bend in such a way that, like, right on top of this locus here, that would be the conic, the tropical quadric corresponding to this polynomial. If I change this first coefficient from 1 to -1, then it's like I'm decreasing one of these affine functions and shifting it downwards by 2. And then what happens is that the break is not going to happen in this way anymore, but like they match in different ways. And now you see the edge in the middle, it goes from having slope 1 to having slope -1. And so really there's a lot of interesting combinatorics is what my point with this example, that tropical hypersurfaces are really, well, they're polyhedral complexes. They're built of these polyhedral pieces. They're kind of linear things glued together. And they're combinatorial in the sense that they have very, like the directions are not completely random, right? Like we always see these vertical directions, horizontal directions, diagonal directions, and they have a lot of combinatorics inside. They have a very rich combinatorics. Those are tropical hypersurfaces. So that's the purely tropical introduction. But why is it that mathematicians got interested in studying these tropical varieties? Well, it turns out there's a very tight connection with classical geometry and classical algebraic geometry. And for that, let me tell you, let's fix a field. So let K be let's say it's algebraically closed field, and I want it to be a valued field. So a valued field means that it comes with an extra valuation map that I'm going to denote by val. A valuation map is just a map that takes elements of your field and it produces tropical numbers. It's kind of a logarithm. It's a valuation in the sense that the valuation of a product of two elements in the field is the tropical product of the valuation, so the sum of the valuations. The valuation of a sum of two elements in the field is at least the minimum of the two valuations. Generically, it's going to be the minimum, let's say, but it could be that the valuation actually goes higher than the minimum of the two. And the last axiom is that the only thing that has valuation infinity is the zero element. Okay, so evaluation, yeah, those are the three axioms of evaluation. For instance, let me give you three examples of valued fields, algebraically closed valued fields. The first one would be, well, just any field with the trivial valuation, for example, the complex numbers with the trivial valuation. What is the trivial valuation? The trivial valuation is just take any non-zero element to 0 and take the 0 element to infinity. The zero element always has to go to infinity. That's this axiom here, but just send everything else to 0, and that satisfies the first two axioms. So, and that's a perfectly valid valuation, and it turns out it's still interesting for tropical purposes. A lot of questions really are interesting, even if you think of the trivial valuation. If you're more interested in number theory, for instance, then you might want to consider, let's say, the rational numbers or the algebraic closure of the rational numbers with the p-adic valuation. And this is the valuation that so p is a prime, and then the valuation of a rational number is the largest power of the prime that divides your rational number. Okay, so take the largest power that divides the numerator and subtract the largest power that divides the denominator. That's subtract the exponents of the power, and that's going to be a valuation. It satisfies these properties here. Or another one that is slightly different is the field of Puiseux series. So I'm going to denote that by C double brackets T. What are these Puiseux series? They're formal power series in the variable t. So imagine infinite power series in just one variable t. The coefficients are complex numbers. And the condition is that, well, the exponents of the series of the terms have to be rational numbers, and all of them have to have a common denominator. Okay, so all of them have a common denominator. This turns out to be, for example, the algebraic closure of the field of Laurent series, and that's why all the terms have the same common denominator. What's the valuation in this case? The valuation is just the smallest exponent that you see there. So if you write a power series like this, the valuation is the smallest exponent that you see in one of the terms, with non-zero coefficient, of course. And then, well, what if you have a polynomial in one of these polynomial rings with coefficients in k in your valued field? You can always tropicalize that polynomial. So you can tropicalize it and turn it into a tropical polynomial that I'm going to call trop f. And how do you tropicalize the polynomial? You just substitute whenever you see addition, just make it tropical addition. Whenever you see multiplication, make it tropical multiplication. And whenever you see a coefficient, an element in your field, apply valuation to it. Just turn it into a tropical number by applying the valuation. Okay. So I'm going to have an example of this in a second, but that's how you tropicalize one polynomial. Now, how do you tropicalize a variety, a zero set of an ideal, a geometric object? Well, let's say you have V, the zero set of an ideal J. How do you tropicalize V? Well, first tropicalize all the polynomials in your ideal, all the polynomials that define your variety. So that's what I'm going to call trop J, is the set of all tropicalizations of the polynomials that were already in J, that were in J. Tropicalize them using this recipe of turning everything into tropical numbers. What you get here is going to be an ideal, but now in the tropical polynomial semi-ring. So it's a bunch of tropical polynomials, and they are closed under tropical addition, and they're closed under tropical multiplication by tropical scalars, and closed by multiplication by any tropical polynomial. And now what's the tropical variety? What's the geometric object that you want to associate to this? Well, it's this minimum attained twice condition. So the tropicalization of the variety is now going to be the intersection of all the hypersurfaces, all the zero sets of all the polynomials here in trop J. So require that the minimum is attained twice for all polynomials in trop J. And just because I want to be more explicit about this and hopefully to give you more intuition, here's a very silly example where, let's say, our valued field is Puiseux series so Puiseux series in the variable t. The ideal that defines our geometric object, our algebraic variety, is generated by one polynomial, one linear polynomial in two variables. So x minus ty. T, remember, t is not really a variable. T is an element of the field. No, t is the Puiseux series. So this is the coefficient here. T is the coefficient, and y is the variable of the polynomial. So this is a linear term and plus one. This defines a line. The zero set of this ideal is a line in two-dimensional space. Well, it's the line x minus ty plus 1 equals 0, a line in two-dimensional affine space. How would you tropicalize that line? Well, you take your ideal J and look at all the polynomials in there. All the polynomials in there. There's the generator. There's x times the generator, y times the generator, and also some combinations of this one. I think this one I created here is this one minus that one, I believe. Yes. So you take the second one minus the third one, you get the one I wrote fourth in that list. And of course, there's infinitely many polynomials in there, but what you do is you tropicalize each of these polynomials using the recipe of turning addition into tropical addition, multiplication into tropical multiplication, and substitute coefficients by their valuations. So for example, this one in the middle would become x squared becomes tropical x squared, minus txy becomes 1xy. And that's because I substitute the minus t by its valuation. Valuation is the smallest exponent you see, that's 1. xy becomes now the tropical monomial x times y. And then the last term is just plus x, and that's the plus x. You do that for every polynomial, and then you require that the minimum needs to be attained twice for all the polynomials that you got here after tropicalizing. And because this ideal was principal, it was generated by just one polynomial, it turns out that this minimum attained twice condition is redundant for everything in the ideal, in the tropical ideal, except for the first one. So the first one already implies all the others. And we already saw how these kinds of tropical lines look like. The minimum between x, 1 plus y, and 0 attained twice. Well, it's a minimum of 3 affine functions, and they bend over some locus like this. So this would be the tropical line that you get by tropicalizing this classical line. And this is a process that allows you to turn classical algebraic varieties into tropical algebraic varieties. Turn classical algebraic varieties into polyhedral objects that are quite combinatorial. Okay. So what's the good thing about this? The good thing about this, maybe the definition of tropical zero set was not supernatural, but it is the right definition in the sense that, well, for many reasons, but it preserves a lot of information about the algebraic varieties. For instance, here in the left, I'm showing you what you could get as the tropicalization of a classical curve of genus 3 of degree 3 and genus 1 in the plane, in P2 or A2. And the fact that you started tropicalizing a curve, a one-dimensional algebraic variety, means that the polyhedral complex you're going to get here is one-dimensional. So this is very important and very useful. Tropicalization preserves dimension. It takes the dimension of your algebraic variety and preserves it and gives you the polyhedral complex that you get has the same dimension as the algebraic variety you started. So here I know this was a curve because it's a one-dimensional polyhedral thing. It allows you to recover the degree. I know that this was a curve. It comes from tropicalizing a curve of degree 3 because the degree tropically you can see, for instance, as the number of vertical rays or horizontal rays or diagonal rays. That's the fact that we have 3 going in each of these directions is the fact that we are tropicalizing something of degree 3. And we can also see that what we were tropicalizing was a curve of genus 1 because actually the polyhedral complex that we got here has genus 1. It has like one hole there in the middle. And tropicalization, at least generically for generic algebraic varieties, it preserves the genus for curves. Okay. So really it turns it into a much simpler, let's say a simpler mathematical object, a combinatorial object, but you still can try to understand these objects and try to investigate these tropical varieties to recover information about the original algebraic varieties you had. For instance, Besou's theorem also holds tropically. If you take the orange is a cubic curve, a curve of degree 3, and you intersect it with a tropical conic, a curve of degree 2, then, well, classically, you know that you're going to have 6 intersection points in projective space. And tropically, that's going to be the case, at least if you count them correctly with the right multiplicities. And if you intersect a cubic with a conic, you get 6 points. And I'm showing you the 6 points there. So a lot of things behave nicely under tropicalization. And let me give you one concrete application that was very interesting in the history of tropical geometry, an application to counting something called severity degrees. And I would say that this is maybe the application or the point where tropical geometry started becoming really useful, and it really took off because people realized that it could be applied to these kinds of problems that were open before. So what are these severity degrees? The severity degree n d delta. So there are 2 parameters here. D stands for degree and delta for number of singularities. Okay, so there's going to be for any d and any delta, the severity degree of the complex projective plane is, well, it's the number of plane curves of degree d and delta nodal singularities, delta self-intersections. Of course, there's infinitely many of those, infinitely many curves of degree d and delta nodal singularities in the plane. But if you impose the condition that they need to go through these many points that you fix in the plane, then you're going to get only finitely many of them. Okay? This is the right number of points that the right number of conditions that you need to fix so that you actually get a finite count, a finite non-zero count. Okay. So let's do some examples to make sure we understand what these severity degrees are. N20 would be the number of degree 2 curves, that's the 2, having 0 singularities, so smooth quadratic curves, or smooth conics, going through, if you compute this number, that's going to be 5, so going to 5 fixed points in the plane. The question is, how many conics go through 5 points in projective space, 5 fixed points in projective space? Well, just 1. Yeah. So N20 would be 1. How about N21? N21 would be the number of conics as well, so quadratic curves, conics, curves of degree 2, but now having 1 self-intersection, one nodal singularity. And now if you compute what this number is, this is going to be 4 points. So you fix 4 points in the plane, and you are asking how many conics having 1 self-intersection go through the 4 points. Well, if you think about it, how can a conic have a self-intersection? It really needs to be a union of 2 lines. It really needs to be the generation of your conic into a union of 2 lines. And in how many ways can 2 lines go through 4 points? In 3 ways. So that's the picture I have here on the right. If those are your 4 points, those 4 corners, there's really three ways in which you can draw two lines going through them, either the two blue ones, or the two green ones over here, or the two purple ones, the cross. And those are the three conics that would go, the generic conics that would go through the 4 points. So N21 is 3. And this really makes sense for any d and delta. So N31, for instance, now would be counting number of cubics now, curves of degree 3 in the plane, going through, well, having one self-intersection going through 8 points. Turns out there's 12 of them, and so on and so on. And these numbers really grow very quickly. They get quite large. And the theorem of Mikalkin that is very celebrated, and it really made, as I said, it made tropical geometry be very interesting for a lot of mathematicians, is that Mikalkin has proved this correspondence theorem, saying that these classical numbers that mathematicians cared about, the severity degrees that are purely classical invariants of the plane, they can be computed tropically, in the sense that you can try to pose the same problem but tropically. How many tropical curves of degree d having delta self-intersections go through these many generic points, and if you count them correctly with the right multiplicity, you're going to get exactly the same numbers. Okay, so if you count, here's an example of how you would need to count for this N31. N31 is, you would need to count a tropical cubic curve going through 8 points, having one self-intersection. So this is an example of something like that. And there should be 12 of these tropical cubics satisfying these conditions, if you count them with the right multiplicity. Because we know what Mikalkin proved is that the classical answer and the tropical answer are exactly the same if you count them right. And this really accelerated a lot of what we knew about these severity degrees, because hopefully you believe that counting this problem tropically, counting tropical curves satisfying this condition, really becomes a simpler, or at least it was simpler for mathematicians to understand how many tropical curves go through these many points and have these many self-intersections than what we were doing before. So for instance, there was this conjecture of Di Francesco and Itzigson in 1994 that was a theorem by Fomin and Mikalkin it was proved using tropical techniques. The conjecture was that these severity degrees, ND delta, when you fix delta, so keep the delta fixed and let the degree vary. Keep the number of intersections, self-intersections fixed, and let D vary. Then for large enough D greater than 2 times delta, this actually is a polynomial. It agrees with a polynomial in D. Okay, so the answers that you get, the numbers that you get as results when you let D vary, they actually are the values of a polynomial in the number D. And this was conjecture in 1994, and actually we knew examples of these polynomials from way before. So for instance, ND1, if you know a bit about this is really measuring the degree of the discriminant of a degree D curve in the plane, and we knew that this degree was 3D minus 1 cubed. And then Cayley knew what this polynomial was for when delta equals 2, and we knew for delta equals 3. Delta equals 4, 5, and 6 is a much more recent thing. Like 150 years later, we discovered what these polynomials were for 4, 5, and 6. Then in 2001, 7 and 8, we understood the polynomials for 7 and 8. And then tropical geometry came, and in 2010, using these tropical techniques of trying to make the count tropically, but not like counting these tropical curves. And that reduces, in the end, it reduces to counting some combinatorial things, like some graphs. You can encode this information. You can even combinatorialize it further and reduce it to counting some kind of graphs like this, with some colors on the vertices and some conditions on the edges, satisfying some properties. And if you count them right, you're going to get the right numbers, the right severity degrees. So using tropical techniques and a computer, we were able to compute, Bloch was able to compute these polynomials for 9, 10, 11, 12, 13, 14. And there's an algorithm for computing them in general, but that's as far as he got then. And well, yeah, this is just to conclude this application. I'm telling you a very particular example of how people have used tropical geometry to solve some questions we cared about in enumerative algebraic geometry, but there's many examples of this, and I'm just mentioning some here. Like, for instance, you can try to do the same type of counts, but not on the plane, not a complex projective plane, not on the complex projective plane, but in more general toric surfaces. And this was done by Ardila and Bloch, and they also showed that for example, this becomes a polynomial with large N of D. Or you can try to count another invariant that people care about, double Hurwitz numbers, now associated to this. This is counting like, well, yeah, it doesn't matter. Curves of genus G that ramify with a map to P1 that ramify in some ways correspond to some permutations. And these are some invariants that people care about, but you can also make the count tropically, and you're going to get the same numbers. So, and it turns out that it's much easier to understand them from a tropical point of view. Or these Walsh-Singer invariants, which is a similar count to what we're doing, but now for real curves. So all this, yeah, this is still up to this day. People are working on these things and trying to use tropical techniques to come up with applications to solve problems that people cared in enumerative algebraic geometry. Okay. So this was my introduction to tropical geometry, and just to give you a flavor of what the field is and one application that really pushed tropical geometry to the place where it is today. And now the rest of the talk, my 15 minutes that I have left, I'm going to try to tell you a bit of what I've been thinking about with regards to coming up with algebraic foundations for tropical geometry. So the point is that, well, at least at the beginning of tropical geometry, it started, let's say, in the early 2000s, like 20 years ago. And well, people were really studying these tropical varieties as purely geometric objects, as polyhedral objects, like the kind of pictures that I was showing you. But of course, when we do algebraic geometry, we have two worlds, and we have the geometric world, but we have the dual world of algebra. And really this, since Grothendieck, this is a very essential way of how people think about algebraic varieties. And we would like to do something like that for tropical geometry as well. So in particular, for instance, we would like to talk about tropical schemes and not only tropical varieties. One curious thing that happens in tropical geometry is that tropical varieties do not have a unique irreducible decomposition anymore. For instance, here I'm showing you a tropical variety, and you can decompose it into irreducible tropical varieties in two different ways. You could decompose it as a union of this one and this one. This is like a line, one of these lines that we have seen already, and a conic. Or you could decompose it as a union of these three lines. And these are really two different irreducible decompositions. And as varieties, you really cannot distinguish. As varieties, the union of these two is the same as the union of these three. They're just this polyhedral complex here. But if you had some kind of algebraic structure attached to it, instead of just this as a subset of two-dimensional tropical space, but if you had some kind of sheaf of functions on it, or then maybe you can, different algebraic structures would allow you to distinguish if you want to think of your variety as this, or maybe as this one irreducible, like without being decomposed into any reducible components. Just a curiosity of something that happens in tropical geometry. And well, one idea would be, how about we try to do algebraic geometry, or like study the algebra of this polynomial semi-ring, the semi-ring of tropical polynomials that I'm denoting by R bar together with the variables x1 and 2xn. But the thing is that really this semi-ring of tropical polynomials is too large. There's lots of ideals there that you don't want to consider. A first problem is that this semi-ring is not Noetherian. And even ideals that you get by tropicalizing these classical ideals. So remember, we have this process for turning polynomials into tropical polynomials, and then you can turn ideals into tropical ideals, into ideals in this tropical semi-ring of polynomials. And even if you tropicalize something as simple as x, the ideal generated by x minus y, well, what that means is you tropicalize all the polynomials that you see inside this ideal. So for instance, if you tropicalize the generator, you get x tropical plus y. But in here you have x squared minus y squared as well, is an element of this ideal. So when you tropicalize that, you get x squared plus y squared. In here, in the classical one, you have x cubed minus y cubed. So tropically, it becomes x cubed plus y cubed, and so on. And you get all these infinitely many. And even though classically x squared minus y squared, x cubed minus y cubed, they're all multiples of x minus y, because really there is some cancellation when you take some multiples of x minus y. Some monomials can cancel, and you end up just with x to the n minus y to the n. Tropically, there's no cancellation, right? Remember, there are no additive inverses. This is an idempotent semi-ring. So x squared plus y squared tropically is not a multiple of x plus y, or x cubed plus y cubed is really not a multiple of the previous ones. And really, tropically, you get this infinite list of generators that you would need for your ideal. So this is not the theorem. Ideals are not finally generated. But much worse than that, or a consequence of that, I guess, is that varieties of arbitrary ideals in this tropical semi-ring of polynomials might not really look like these polyhedral pictures that I'm talking about, but they might really be like infinite intersections of polyhedral things, and an infinite intersection of a bunch of polyhedral straight flat things might be very not flat. It might be a circle, it might be something that has not much structure at all. So I would say that by studying general ideals of the semi-ring of tropical polynomials, you really are leaving the realm of tropical geometry. You're not dealing even with polyhedral complexes anymore. You're dealing with a much more complicated thing, and maybe we don't want to do that. So that's when we introduce this notion of a tropical ideal. This is like a class of ideals consisting of tropical polynomials that are well behaved, that we'll still want to consider, that still fit into the realm of tropical geometry. And the inspiration, like the motivation for that definition, comes from thinking about, well, if you are dealing with polynomials where the coefficients are in a field K, and if you truncate your ideal, so let's say J is an ideal in a polynomial ring over a field, and you fix a degree D, then you can truncate your ideal at degree D, meaning take all the polynomials in your ideal that have degree at most D. So the degree of f is at most D. Then when you truncate it, you really get a linear subspace. You can add these polynomials and get another polynomial in there. You can subtract them. You can multiply them by scalars. So you get a linear subspace of the space of all polynomials of degree at most D, which I'm going to denote. Well, I'm going to identify with your field to the number of monomials of degree less than or equal to D. So this is just my notation for the space of polynomials of degree at most D. And the ones that are in your ideal are a subspace of all of those. Well, let's try to mimic that definition for tropical geometry. So that's what we did in 2016. We said that an ideal in this polynomial semi-ring of tropical polynomials, we're going to call it a tropical ideal, meaning it's like nice for tropical purposes. It's still within the realm of tropical geometry. If whenever you truncate it, whenever you take all the tropical polynomials of degree at most D in your ideal, what you get is what we call a tropical linear space in the space of all tropical polynomials of degree D. And what I'm using here is a technical term. This is, I'm going to define it here, but it's not going to be so enlightening, maybe. A tropical linear space is really this fundamental concept that we have in tropical geometry of what are the linear subspaces in tropical geometry. They're called tropical linear spaces, and they're very related to matroids. If you have heard of that, valuated matroids, they're really very combinatorial things, and they play the role of linear subspaces in tropical geometry. It's really a much stricter condition than just being a module over the tropical numbers. It's much more than just being able to add two things and getting something in there, or multiplying by scalars. It really has to have some combinatorial properties, and that's called coming from the matrix. One way of saying it, although maybe if it's the first time you see this, it's not going to be so enlightening, is that an ideal is going to be a tropical ideal if you can eliminate monomials, if it satisfies this monomial elimination axiom. So the axiom is that whenever you take two polynomials in your ideal, f and g, and let's say there's some monomial where they have the same coefficient, this is my notation for the coefficient of f at the monomial x to the u, and this is the coefficient of g at the monomial x to the u. So if both coefficients are the same in the same monomial, then there should be some way of eliminating that. Think of classically, you would like to take the difference of the two polynomials and get a polynomial that doesn't use that monomial. Well, we're going to kind of impose it here as an axiom. Whenever you take two polynomials in I with the same coefficient in a monomial, in the same monomial, then there has to be some third polynomial in your ideal where that coefficient is now infinity, the additive identity. So that coefficient, that monomial disappears. And the coefficients of all other monomials are at least the minimum of the coefficients that you saw in F and G. And for this to actually be an if and only if, I need to require that this inequality here is an equality whenever these two coefficients were different. Okay, oops, sorry. Yeah, so there is some purely combinatorial axiom that we're imposing on our ideal, and it comes from matrix. It comes from these combinatorial objects that govern what the tropical linear spaces are in tropical geometry. So yeah, so yeah, maybe if you don't interiorize the whole definition, just think that tropical ideals are going to be some special class of ideals in the tropical world that satisfy a nice combinatorial condition, very natural combinatorial condition, and that makes them have a lot more structure than just any ideal. Just, I think I still have some time, so let me just, some examples here. For example, the tropical ideal, the ideal generated by just one tropical polynomial x plus y would not be a tropical ideal because, well, in degree 2, you would have x times this generator, that's x squared plus xy. You would have y times this generator, that's xy plus y squared. But now you have these two polynomials, x squared plus xy and xy plus y squared, that have a common monomial, xy, with the same coefficient. So there should be some other polynomial that eliminates that monomial. So something that doesn't use the xy, and it only uses x squared and y squared. So you would have to have x squared plus y squared if this was a tropical ideal. But as we saw before, x squared plus y squared is not multiple of x plus y. So really, that's why this is not a tropical ideal. But we still get a lot of nice ideals. In particular, all the ones that come from tropicalizing a classical ideal. So whenever you do this process to a classical algebraic variety, you tropicalize the ideal, defining the variety, and you get something that satisfies these combinatorial properties. So any ideal, the form tropicalization of a classical ideal, turns out to be a tropical ideal. And these we want to think of as the realizable ones, the ones that come from, that you can realize as coming from some classical object, classical ideal that you're tropicalizing. But already when we define this, we realize that there are really non-realizable tropical ideals. So there are lots of these ideals in the tropical world satisfying these combinatorial conditions that you can never obtain as tropicalizations of something classical, of some ideal with actual coefficients over a field. And that makes the theory very interesting and very combinatorial. It's quite deep, the combinatorics. Let me just tell you some nice properties of why this is a nice class of ideals to consider. So for instance, you can define Hilbert functions for these tropical ideals. And the Hilbert function of an ideal satisfying of an ideal, a tropical ideal, so an ideal, the tropical polynomials with this combinatorial condition, is the function that to every degree, so to every degree d, it records what the codimension of the degree d part of the ideal is in the space of all polynomials of degree at most d, all tropical polynomials of degree at most. And in order to talk about this codimension, you really want to have this matrix condition. This combinatorial condition make this notion of codimension quite nice and natural. And that's what allows you to have a notion of Hilbert function. So you would not be able to do this so nicely for general ideals. Just for tropical ideals, you can define this Hilbert function. Let me just remark that this is a generalization of how we define Hilbert functions for classical ideals, in the sense that if you have a classical ideal, it has a Hilbert function measuring the codimension of the ideal in the space of polynomials of every degree. And you get the same Hilbert function before tropicalizing than after tropicalizing. So yeah, so this definition is compatible with the usual notion of Hilbert function for ideals. What we proved is that even if your ideal is not realizable, even if it doesn't come from a classical ideal, you still have this behavior of the Hilbert function that for large values of d, it becomes a polynomial in the variable d, in the degree d. Okay. So really, any tropical ideal, whether it's realizable or not, has a Hilbert polynomial. This polynomial is called the Hilbert polynomial of the ideal. It's the one that measures how quickly the degrees are growing when you increase, the codimensions are growing when you increase the degrees, the truncations that you're looking at. We also proved that, remember, one of the problems was that this semi-ring of polynomials, of tropical polynomials, was not Noetherian. You could have polynomials that are infinitely generated. Well, when you restrict to this class of tropical ideals, you recover some kind of Noetherianity in the sense that now you cannot find an infinite ascending chain of tropical ideals anymore. Like each of these is infinitely generated, typically, is not finitely generated, but still you would not be able to construct an infinite ascending sequence of tropical ideals, which is very nice if we want to do algebraic geometry. It really means that we might have some notion of dimensions, or like we really have some control about what the ideals look like. And because I'm running out of time, let me start going slightly quickly. I have this and one more slide. More recently, we started trying to understand better the connection between the algebra and the geometry. So as I said, every tropical ideal has a Hilbert polynomial, and the degree of that polynomial is what we can call the dimension of the ideal. So what degree of polynomiality are these codimensions growing as? That's the dimension. And then in 2016 and later in a paper in 2020, we proved that, first of all, we recovered this essential thing that we wanted for being in the tropical geometry realm, meaning that the variety of any tropical ideal is a finite polyhedral complex. Okay? This was essential for us. We really want to be dealing with finite polyhedral complexes, with polyhedral things, and that happens for tropical ideals. And in fact, the dimension of that polyhedral complex as a polyhedral complex is really equal to the dimension of the ideal as an algebraic object. So it's the exponent of the Hilbert polynomial. This is something that classically holds for ideals, but for classical ideals, but we also have it in the tropical world. And even better, if you know a bit about tropical geometry, there's this essential condition that all tropical varieties are balanced polyhedral complexes. All the rays cannot be on like one side of the board. They really have to spread out and satisfy some zero tension condition around every face of codimension 1. And that is the case for varieties of tropical ideals, even if the ideal is not, if the ideal is not coming from a classical ideal, it still has to satisfy this property that is essential for tropical varieties. It's a balanced, finite polyhedral complex, and the dimension is the algebraic dimension of the ideal. So there's lots of nice properties that are a hint that this might be a nice object to have as an algebraic foundation for tropical geometry. And my last slide is just some future directions, some open questions that we have and we're working on right now. A lot of the things we care about, I mean, one of the main problems with tropical ideals is that there are not so many tools for dealing with them. We're really missing some commutative algebra tools for dealing with them, like sum and intersection don't work well for tropical ideals. If you take two tropical ideals and you just add them or intersect them, they might not be tropical anymore. They might not satisfy this combinatorial condition. So we're still figuring out how to come up with good notions of this. What is a prime ideal? That's not completely clear. What's a prime tropical ideal? That's not clear. What would be primary decomposition? What's a free resolution for a tropical ideal? All these are things that are not developed yet. And of course, it would be very useful to have something like that for working with them. Another question is, how general can these polyhedral complexes variety of a tropical ideal be? We know that they have to be balanced polyhedral complexes, but how general? And in a paper with Jan Dreisma, we proved that actually not every balanced polyhedral fan is of the form variety of a tropical ideal. And this boils down to some matrix results that people in matrix theory knew already. Or how do I describe a tropical ideal? Finally, how do I email you a tropical ideal? It's not so clear how to do that because it's like really infinitely many information. So this is something I've worked with my student, Nick Anderson. And yeah, let me just because I'm running out of time, let me not say so much about this, but this question of how can we like encode the whole ideal in just finitely much information that's not completely clear yet how to describe, because there's no notion of generation. Remember, all these tropical ideals are not finally generated typically, so I don't want to have to tell you a list of infinitely many generators to tell you the ideal. Maybe there's some better way of describing them. And the last thing I wrote here is some kind of Nullstellensatz. Is it true that if the variety of a polynomial contains the variety of an ideal, is it because a power of the polynomial actually lives inside the ideal? This is something that I've been working on very recently, and I think the answer is yes, together with Diane McLagan, but we're still finishing out the details. So yeah, I've run out of time, and thank you for listening.
Thank you, Felipe. We are now open for questions or comments. You can raise your hand or write on the chat. Okay, we have
Profesor Andrés Villaveses, chicos.
some.
Hello, hola Felipe, hello.
Andres.
Thank you, Felipe, for this. Can you hear me? Sorry, I don't know if the mic is working well.
I can hear you.
Okay, thank you. So thank you, first of all, Felipe, for this wonderful introduction and all these questions that seem so interesting and so hard, some of them. I just have, one question that will reflect my ignorance of this is there some kind of, if you look for algebraic versus geometric approach to this subject, at some point one would like to balance them through some sort of a, understanding the class of all possible extensions on the one hand of the varieties here in this case, and on the other hand, somehow controlling. Are there any like groups that control them? Is there some kind of Galois theory for these at work by anyone, or is there some kind of a attempt of trying to create some kind of universal object or large object that would control somehow all of these, like maybe super Metroid of some sort, or some kind of limit, like analog to what happened with Galois theory and classical varieties?
Yeah, we're definitely not at that point yet. It would if you think about, as I was saying, if you just think about all possible ideals you can get without imposing any restrictions, you really get a lot of them. And I expect there is really not a well-behaved Galois theory at all, and you cannot control things. But maybe if you go to the right category, if you fix your framework at the right place, I'm sure there are some interesting things to say. We're not there at all yet, but yeah. I would definitely love if more model theorists got interested in this and could contribute.
Yeah, it feels very more theoretic in some sense, but at the same time, it is fascinating that it has this purely, combinatorial flavor. You have all these polynomials and these numbers that you can actually see so many things. But at the same time, I think the fact that they are not finitely generated, your ideals, makes them, really, well, not necessarily complicated, but different from a usual more theoretic. And I just want to mention that, especially nowadays, mole theory is kind of awakening to, or reawakening to, possibilities of dealing with infinitely definable, where you can somehow, even if you have infinitely many generators, in some cases, you can boil them down to finite or to small in some sense. And this may be, a natural source of a very good examples. I think your last slide had many questions that seem to be very, provocative to us as model theorists.
Yeah. No, I agree. So maybe to approach this from a model theoretic point of view, you would really have to have a framework in which you allow, as you say, sets that are defined by not by a finite formula, but some more things. And then I would love if you could tell me more about it at some point.
Yeah. Well, thank you very much. It's fascinating and totally new for me in many ways. I mean, I had heard about this, but never in this, this clarity and in this way. Thank you.
Thank you.
Okay, we have another question from Sergio. Okay.
Can you hear me? Yeah?
Yes.
I don't know if I can make the question in Spanish or is better to have made it in English.
Spanish is fine for me, yes.
Ok, ya, perdón, sí, es que así, son dos preguntitas así sencillitas, rápidas. La primera es, ok, yo he visto un poquito sobre teoría de esto de geometría tropical, pero yo lo había visto cuando definían con la suma con el máximo. ¿Hay alguna diferencia o es lo mismo? ¿Es como la misma definición o...?
So let me translate the question just in case there's people who don't speak Spanish. The question is, what happens if instead of using min, we use max as the tropical sum? And the answer is that it's really the same. They're completely isomorphic structures. If you use max, then you want to add minus infinity as your additive identity, but it's really the same thing. So it's a matter of choice, and I would say half of tropical geometers use the min convention and half of tropical geometers use the max convention, but it's really the same.
Okay, thank you. Well, the second one I can't make it in English. So you have the monomial elimination option, and this option, sorry, is equivalent to half a matroid, or is like a similar of the definition of a matroid?
It's exactly being a matroid, yes. So I have it here. I mean, it's what is called a valuated matrix. In exactly this context that I put it here, it's what is called a valuated matrix. So it's a matrix, but you have some coefficients on the matrix.
Oh, okay.
They correspond to like the coefficients that your polynomials are going to have. And it is equivalent to state this monomial elimination axiom to saying that your set of polynomials are the vectors of a valuated matrix. Yeah, it's exactly that.
Okay. Thank you so much.
All right.
Okay, we have another question, but we think we are over the time. Camilo, you can consider email Professor Rincón, could be.
Yes.
Time, Spanish. Una pregunta. ¿Puedo alguna conexión conoces sobre politopos de flujo y la parte de combinatoria? Porque hace unos días miraba que hacían, digamos, un dual, ¿sí? Entonces, básicamente lo que hacían era, en vez de llevar el dual a todas las aristas, se restringían a algunas aristas. Sin embargo, lo que hacían era, al final del día, pues asociarlo a un grafo. La pregunta es si al hacer ese dual, uno podría, pues, pasar la geometría tropical y o nuevamente volver a recuperar propiedades combinatorias, sin pasar por el grafo.
Respondo rápido. Sí hay una conexión entre estas cosas. No realmente lo que estaba hablando yo ahorita, pero sí hay una forma, geometría tropical, dado que es trabajar con mínimo y suma, es posible modelar ciertos problemas de flujo en términos tropicales y muchos objetos que son importantes para la geometría tropical vienen de estos politopos también, politopos respondientes a matroides o politopos de flujo. La conexión no es tan directa, pero sí se usa una rama en la otra. Sí hay como conexiones que uno puede hacer. Sí.
Muchas gracias.
Okay, thank you, Felipe. We are going to the next talk.
All right, thank you, everyone.
Very interesting talk. We can start now.
Ok, muy bien. Profesor Quintero.
Muy buenos días, ¿cómo están?
¿Cómo
¿Escuchan
estás,
bien o no?
profesor? ¿Te escuchamos bien?
Yes.
Ok. Muy bien, profesor. Entonces la idea es introducirlo primero algunas palabras en español, otras en inglés por Jessica y luego vamos con tu presentación. ¿Puedes compartir la pantalla?
¿Se ve la pantalla?
¿Se ve, profe? ¿Quieres ponerla en full screen, en pantalla completa?
¿Está bien ahí? Sí, ¿no?
Está muy bien.
Ok.
Listo. Okay. So we will present Professor Quintero, some words in Spanish, other in English, for the people that is connecting from outside of Latin America. So, buenos días para todos los que nos acompañan a esta hora. Para mí es un gran placer poder presentar a uno de mis mentores en matemáticas, a una gran persona y amigo. Él es el profesor José Raúl Quintero.
Good morning to everyone. It is a great pleasure for me to be able to introduce one of my mentors in mathematics, a great person, a friend. He is Professor Raúl Quintero.
El profesor José Raúl Quintero realizó sus estudios universitarios de pregrado y maestría en la Universidad del Valle en 1984 y 1988 respectivamente. Luego se vinculó a esta misma universidad como profesor asociado y durante una comisión de estudios viajó a Estados Unidos a realizar su doctorado en la Universidad de Maryland, College Park, donde obtuvo su título bajo la dirección del profesor Bob Pego, con su trabajo Two-Dimensional Slattery Waves for a Beniluk Equation. Seguido a eso regresó a Colombia y desde allí continuó como docente e investigador. En su posesión como miembro correspondiente de la Academia Colombiana de Ciencias, me permito citar a Jaime Lesmes, quien estuvo a cargo de la ceremonia, un gran matemático colombiano que entonces describió la tesis de Raúl como un trabajo adelantado a su tiempo.
Professor Quintero completed his bachelor and master in 1984 and 1988, respectively, at Valle University. Then he became an associated professor at the same university. In the modality of study commission, he went to the United States to pursue his doctorate at the Maryland University College Park, where he obtained his degree under the direction of Professor Bob Pego with his thesis, Two-Dimensional Solidarity Wave for a Beniluk Equation. After that, he returned to Colombia and he continued teaching and his work as a scientific researcher. In his position as a corresponding member of the Colombian Academy of Science, he received statements as a work ahead of his time, describing his thesis under the words of the Jaime Lesses.
El profesor Quintero tiene importantes publicaciones en el área de las ecuaciones diferenciales parciales, análisis no lineal, física matemática, entre otros. Ha ocupado importantes cargos como vicedecano de investigaciones y director del posgrado en ciencias matemáticas en la Universidad del Valle. Aquí su rol fue de gran importancia al impulsar la creación del doctorado en matemáticas. Actualmente es decano de la Facultad de Ciencias Naturales y Exactas y director del grupo de investigación, ecuaciones diferenciales parciales y geometría, donde ha liderado diferentes proyectos de investigación.
Professor Quintero has important publications in the area of partial differential equations, nonlinear analysis, mathematical physics, among others. He has held important positions such as a Vice Dean of Research and Director of the Postgraduate Program in Mathematical Science at Valle University, and his role was of great importance in promoting the creation of the doctorate in mathematics. He is currently Dean of the Natural and Exact Science Faculty and Director of the Research Group Partial Differential Equations and Geometry, EDPG, where he has led different research projects.
Los invitamos a disfrutar de la charla del profesor Quintero y a las 12:30 en hora local de Colombia a disfrutar del tributo que en esta conferencia hemos organizado en honor a su carrera. Muchas gracias.
Please enjoy Professor Quintero's talk. All participants are invited to attend the virtual ceremony. We are going to honor his career at 12:30 in Colombian time and 7:30 p.m. in Central European time. Thank you. Go ahead, teacher.
Ok, gracias. Primero unas palabras en español. Muchas gracias al comité organizador, especialmente a Duan, pero también a Jessica, a Milton, a Brian, a Karina, que han hecho un trabajo extraordinario al convocar pues, investigadores de la talla de Simon Donaldson, Terence Tao, Carlos Kenny, profesor Suazúa, entre otros. Es decir, este es un evento de mucho nivel. Realmente es un honor poder dar una conferencia aquí, aunque yo presioné un poco a mi querido amigo Duan. Bueno, y pues con respecto a lo que menciona Duan, pues yo creo que una de las misiones de un profesor es, digamos, impulsar a sus estudiantes, independiente de si son avanzados o no. Todos somos genios en el fondo, entonces uno tiene que impulsarlos, insistirlos en que continúen su camino y lo van a encontrar. Entonces, lo que ha pasado con todos estos estudiantes es que han seguido su intuición y han seguido su camino, y algunos los hemos apoyado un poco, pero todo eso lo han hecho ustedes mismos. Okay, thanks for the invitation to give this talk, especially to the Science Committee and Duan Cardona for this invitation. So, as were mentioned, my work is related with partial differential equation, especially dispersive models. And in this occasion, I'm going to talk about an equation that appears in my thesis. And this model is a valid approximation for describing small amplitude long order waves in the case of final dip. And it's a very simple equation. It's a 4-order equation, right? And these numbers A, B are related with the surface station coefficient in this model. And I just want to say some few words about this model, and because this model appears in my thesis. So this model is just the 1D version of a 2D model, which is an isotropic model for 3 Fourier waves, where this parameter here, mu, is the long wave parameter, and epsilon represents the amplitude parameter. So we are looking here at solution, and not any kind of solution, but the solutions which are small in amplitude and long Fourier waves. And this type of model appears also in the work by Benny-Luc in '64. They were looking at interaction of traveling waves, and then the model is somehow inside of this computation. The only difference is that in the case of the Benny-Luc model, mu they only use one parameter, which is epsilon, and then mu is 1 over epsilon. So if mu is small, and then 1 over epsilon is large. So we did the formal derivation. This coefficient A and B appears here because when you derive the equation, there is a relationship between the second, the Laplacian, and phi t. So when you have the free to move to interchange Laplacian with phi t. So you get this family of models. And in the 1D case, I'm going to point out that we derive this. If we just put 1D here, we get the previous equation, right? This equation. We don't have to modify anything. But there is another model close to this one, which is the KDV model. So when you derive these models, you have 2 essential variables. One is the free surface elevation, and the other variable is the velocity of the fluid. So in this particular case, the velocity is a potential, it's gradus phi. So you have 2 variables essentially. You have the eta, which is the free surface elevation, and you have the gradient of phi. And then the Kp or the KdV in dimension 1 correspond to the free surface elevation, and this phi here corresponds to the velocity. So essentially, we are talking about the same model, but we are using different variables. So there is a very close relationship between the Benny-Luc model and the KdV or the Kp1 and Kp2 in case of we are in dimension 2. So this number here, depending on this number, you have Kp1, or depending on this number, you have Kp2. So that's the main point. So this model, since this model is isotropic, there is no special direction here. And then this model is an approximation formally valid to describe 2-way water wave propagation, which is different from the KdV case or even the Kp. Because in the Kp case, you have essentially one direction, and the variation in the y direction is weaker than the variation in the x direction. So you have another type of model. But essentially, we are dealing with models to describe the same phenomenon. In fact, we can prove that we can go from solutions to the Benny-Luke equation to solutions to the KP or KDB, depending on the dimension. One particular thing here is that for this model, for the linear part, you look at the linear part of the model here. Right. So essentially, we take out the nonlinear part. There is a well-known equation, which is the Good-Boussinesq equation that corresponds to A = 1 and B = 0. So at the linear level, those equations are the same, right? Those equations are the same. But these models are quite different at the linear level. For example, for this model, for this problem we want to talk here in this talk, we need to perform spectrum analysis for the linear part. And then when you look at the behavior of the eigenvalues in that problem, so the behavior is of lambda k is order 4 with respect to k. But in the case of the Benny-Luke model, so you don't have that growth. So this makes a huge difference between these two models, right? And this one appears when you look at something that we call the gap condition. The gap condition for the Good-Boussinesq equation is essentially infinity, and the gap condition in the case of the Benny-Luke model is limited. So that means that we have to put some restrictions to the time in the problem to talk about controllability. So as mentioned, Professor Suazua, we are embedded in many controls. I mean, our life is driven by controls at any time. So this is a problem that has many applications, right? The techniques, and so controls appears everywhere. Even you are in a room, right? And then you have a fluid in the room, and then you have the questions for let's say the temperature in that room. So somehow you wanna decrease the temperature to some level, you have to use an extra force. You have to put a conditioning to force the system to go to some temperature to your desired temperature. So this is the type of problem that can be solved using this. And even you can think about taking a problem and then forcing the boundary of the model to go from one state to another state. So essentially, that's the main issue here. The control problem that we wanna address is to have a system and then take the system from one state to another state. So somehow you need to impose some conditions. Could be an internal force, or could be to force the boundary in somehow to get the result. Okay. Well, some results regarding this model with my student, Professor Montes. We look at the distributed control for the generalized Benny-Luke equation in a periodic domain. There are many important contributions for Byung-Chul Sang in this area, and especially he has a contribution in the case of the Good-Boussinesq equation. There is contribution from Lyons regarding the Good-Boussinesq equation using the Hilbert-Unix method for this model for the linear case. And you can see here that the control is in the y-x variable, right? So you put this control VT here to force the system to go, right, to one state to another state. Right. And here appears, as I mentioned, to use some restriction with respect to the time and the L, which is the range for the spatial variable. Crepot, Emmanuel Crepot has very important contributions too in this area, and in the case of the linear case, especially this is a generalization of the Lyon's result, but also she has contributions in the local control problem using the Mana contraction fish point. There is a generalization of this work by Amara Olcidi, which is an extension of Crepot's result for the good-business equation. This is a equation with variable coefficients, right? And there is also a result by Eduardo Serpa and Crepot for the bad-business equation, where the sign of one of the four derivatives are go for plus to minus. So in this case, they put something which is called improved the approximated controllability for this problem, and essentially they just put a force, a moving force to control the system. So there are many words. Professor Yvonne Rivas from Universidad del Valle is also working in control problems for many years ago. She is a Bijusan former student in Cincinnati. So there is many contributions in this area. This is just a small one. So the strategy of the proof is just was first to solve the homogeneous linear problem associated with the system. This is the clever one, to perform in detail the corresponding linear spectral analysis and show the observability condition for the homogeneous problem. In this case, we need to use a version of the Ingans theorem, especially with the gap, because in this case, this model is quite different from the good-business equation, where the gap is infinity. But in this case, the gap is finite. And then use the Hilbert unique method, HUM, and also a reversibility condition for this problem. And then essentially the Hilbert unique method essentially is a shooting method in a Hilbert space, right? And then you just solve the problem, and you just shoot and choose the condition to get the right answer. So this is the shooting method essentially. And then in this problem, we see that the controllability, exact controllability, is equivalent to null controllability. To take one system to the zero state. And then once you solve the linear part, then you go to the nonlinear part. And then the method is clear. It just uses the contraction principle, but there are many details to get this contraction. So it's not just straightforward. It has a lot of computations, and it's quite complicated. But still, so the work that I'm going to present here is inspired in Crepot's result for the good-business equation, but the computations are quite different, and some of them are challenging. And the fact that this non-zero brings many problems to prove the result. So the main result is this. Essentially, there are two main results. You have for this fact that T is greater than for L, right? There is a relationship between the
Can you hear something?
that's forces. Yeah.
Sorry that your screen was freezing for some time, but now it's okay. Please continue.
It's okay.
Yes.
Okay.
It's okay.
Oh, it says that my connection is unstable. I don't know what happened. Okay. So, so essentially we are saying here that we can go to one state in phi x. One thing that I want to mention here, this is a world wave model. So as I mentioned to you in the derivation of this model, that phi represents the velocity. I mean, u, the velocity u in the model is grad of phi. So that means that the relevant variable here in this model is not phi, it's phi x, right? So the main variable for this problem are phi x and phi t. So the conditions are imposed in phi x and phi t, no in phi and phi t, which is a little different from the case of the good Gaussian equation. So we want to go to this state to another state. And then the control here is on phi x, which is the first case. And in the second model, so we have two types of controls here. And the second model is to control phi s x with some function b. So essentially we have two problems. And for this talk, I'm going to concentrate in the previous one, in this model. But the techniques and the arguments are essentially the same, with some differences. But essentially, we have the same type of result. And the spectral analysis is quite different in those cases, but still the techniques and the type of argument are the same. But so I'm going to try to show you one part of this problem. So the first step is to use this variable q equal to phi x and r equal to phi t, and then to rewrite the equation as a first order system. So we have our Benelux equation now takes this form, and this is a order one. This b and a are order two, but this is the inverse of this. So this is essentially an order one operator. And then we are going to prove the result first for this type of models. And then at the end, try to go back to our the original model. So for this model, we have the nice reversibility property. You have a solution for this, right? And then you can go to the time t equals 0 to time t capital T. So that's why we can switch to the null condition, which is important. It's an important observation because we have this reversibility property for this model. So when we look at the homogeneous problem, right, we should try to solve this problem, and then essentially we can decompose U as a sum, right, and then plug it here, and then try to solve the problem, the eigenvalue problem by hand. And in this case, that happens is that you try to solve this eigenvalue problem, and then you have to use this domain because you need to import this condition, right? So you import this condition here to your domain. And then what happens is that you have a solution, an eigenvalue problem for this model, and then this is equivalent that the second component is a non-trivial eigenfunction for this operator, which is an order 2 operator with the eigenvalue sigma squared. And of course, one important thing is that this sigma squared must be negative. And the reason for that is that when you compute the equation you use the equations for C and multiply by C or Cx, then you finally get this quantity equal to 0, and then you see that sigma squared must be negative in this case. So And then you have to look at this operator, the inverse of this operator turns out to be compact. And well, we use the fact that this is compact to find a sequence of eigenvalues that goes to 0 as n goes to infinity. So once you have this decomposition, then you can define this space H alpha, which is that so you define that through these sums using this basis, and then this is the norm. So the first observation is, for this problem, this lambda k behaves like k squared. So using that, then we can see easily that H1 script must be H02, and H1/2 is H01, and the dual of this is H minus 1/2. So this is just by looking directly to the behavior of these spaces. So the first case to solve the homogeneous problem is quite easy, because you just solve by each node, you solve the question, and then you can see directly the solution has this form. So keep in mind that gamma k is the square root of lambda k. Recall that lambda k here is positive, right? We write the eigenvalue in this way, minus 1 over lambda k. And then, so those lambda k are the eigenvalues for the operator A. And then you have an estimate of the energy of this solution, which is compared with the energy of the solution at the time t. So that means that the solution holds for any time. We have a global solution in this case. And one important thing that appears in the proposed paper is that somehow we need to describe the eigenfunctions, right? Somehow to be able to compute them. And of course, the fact that B in this case is non-zero brings a little complication, but still we can use the Kaipos approach. So the solutions, this C1 and C2n are eigenfunction has this form. So this coefficient, I mean, this is the technical, but the fact is that we can compute directly where this function C1n and C12 are. So the coefficient is quite complicated. Let me show you 2 more lines. What is the relationship between mu k and nu k? And then so we have these coefficients here, and I had to use this SC and SCH because in the formula it's too huge. And then so the SC is sine y cosine y, and CSHG is hyperbolic sine and hyperbolic cosine. So the relationship between mu and nu is given by these 2 conditions, and somehow this is very important to determine the behavior of the lambda k eigenvalues for the linear mode. So, well, the gap condition. So to use this one of the Inghams theorem, we need to estimate the difference between 2 consecutive eigenvalues, right? And then the happening for b equals 0 in the Goose-Buzynski equation is that this difference is infinity. So this gap is infinity. Here in this model, the gap has to be finite. So that's why we have a restriction on the time t, capital T. So in the first case, capital T must be bigger than 4L because we have this estimate. Well, the relationship between lambda k, the eigenvalues, and mu k are given by this formula. And then this result holds because we just take this function, gy equal to y square root of this quotient, and then when you take the g prime, then you get this number is bigger than 1, when A is bigger than B. And then that means that we can use the fundamental theorems of calculus to get the bound. And that's the proof, essentially. Now, using this gap condition, then we can prove the observability inequality with this restriction on T. This comes from the fact that T must be bigger than this number over P. So that means that's the restriction for T. And then essentially we are saying for alpha equals 0, we are saying that these norms, the QX TL squared is bounded by these two norms, by the same norm. So this is very important in this problem. So this inequality is clever in all the computation that we have to do. One observation is you have a function in L2 that means that the average of W is 0 in 0L. So you have a function whose average in 0L is 0, and then you can define the x derivative inverse of omega in this way. So this function is in fact h1. So we are in the right setting because our variables are qx, are px and pht. So keep in mind this. And then so the first theorem that we have to look, right, to look at the control, try to control the linear problem, right? So this is the linear problem, then we put the control here. We are gonna control q at time t and when x is equal to L. Then, so we have, we just proved that this model has a solution in this space. So the proof of this, roughly speaking, is just to take the equation, multiply appropriately this, integrate, right? And here we use a solution. This solution, this phi at C are the solutions for the homogeneous problem, right? That we described in the previous slides. And then we multiply this and then integrate by parts and do many things. And then you end up with this equality here. And then here you see that here we have the control, right? And then you take q tilde equal to this guy, and phi tilde is, and c tilde is, and then you rewrite your system, your previous equation in this way, right? And then you set this space B is equal to L2 cross H minus 1, and you define this operator. So you here in R0 phi 0 dot, this is a inner product in L2, and in the other quantity you have H1 H minus 1. So you have the dual of H minus 1. So essentially you can write this. You define LS phi S dot in this way. So this part is just an inner product. Where? In the space B prime cross B, where B prime is the dual of B. So essentially, we just use the fact that we have this type of inner product, and then you can prove that there is a solution, a unique solution in this space, right? Okay. So to go back, you just define Q, you solve for Q dot, Q tilde, excuse me. And then your Q has to be the derivative of this one, and then you get the result. So essentially, this is just like a Riesz theorem to get the result in this case. Let me see the time. And now we want to go to the nonlinear case, right? And then excuse me, we're still in the linear case. Let me go back. Okay. Yeah. We still are in the homogeneous case. And then we use the Hilbert uniqueness method and the reversibility property. So to get the result, right? Then so we just gonna go to the one state to the zero state. This is the null condition here, right? So we just prove this, and then we go back to the exact controllability for this problem. So essentially we have this. We need to choose a special Hilbert space to do that, right? And then the proof is very close to previous one. You need to define a special function, right? From B cross R to B prime cross R, which is this way. And then you use the fact that you can solve this problem, the linear problem, but you are imposing the conditions, right? And you wanna go to the null condition, and then well, to prove that this is well defined. So we have a well defined. Putting this in the right form, you get that this like in product is exactly right. The condition this one here is just exactly the condition that appears in the observability condition. So the observability condition means that this capital lambda
Again, I can't hear him.
Okay. Professor Quintero. Sorry, is that we lost your screen,
ya.
maybe.
¿Me escuchas? Sí, se fue un momentico.
Se fue un momento. ¿Puedes compartir de nuevo?
Sí, sí. I'm sorry, man.
Okay, so let's wait for the presentation of Professor Quintero. Some seconds.
Let's see. Can you see now?
Perfecto.
Yes.
Okay, I'm sorry. I don't know what happened. We have a bad connection here. I was saying that we define this capital lambda T, and then the formula for this capital lambda T is that we in the right hand side we get exactly the condition in the observability condition, and then using that we just say that the lambda T is an isoformation from these two spaces. So that's why this is like a shooting method. You just solve the problem, and then you choose lambda capital T at this point to be this one, and then you have the right condition. So you have this phi T, this bar phi rho T in the right space, but then you need to recover, right? Recall we need to recover Q and R. So the way to recover this is just by integration, and then we solve the problem. So essentially we have a machine, right, which is the observability condition that allow us to establish that this lambda T operator is in fact an isomorphism. Then we can solve the problem. That allows us to choose especially that condition lambda T, and this is exactly like the shooting method in infinite dimensional space. And then so now we can go to the nonlinear controllability problem, and then here the standard, let's say the standard thing to do is to use the contraction principle, but again, it's not simple. as saying that it's not. I mean, it's very complicated to get, but still, the only tool here is to use the contraction principle, and then we can go from, you solve the linear problem, then you go to the nonlinear problem using a fixed point argument, and then use the contraction. It's essentially that's the key for solving the problem. So now we solve the problem for the system, the first order system, but we wanna solve the problem for not for the original equation. So when we impose this condition in Q, see, if we assume that our initial data Q, recall that Q correspond to phi x, and then phi x, you integrate phi x, so that integral is 0. So that's why we are allowed to assume that the initial data has average 0 for Q. So once we have this condition, then we can go back using the x inverse to get the right variable. So using this condition in our problem, then we can define phi xt as the inverse, the derivative inverse of x of Q. And then we can prove, in fact, that this is a solution for the Benelux equation. And in the main theorem, we use one Hilbert space. And for the variable Q, we use the H1 space. But there is a direct relationship between the Y1 condition, the 1Y space, and the H1 space. And the reason is that we have this relationship. That means that we can match our initial condition with the initial conditions for the original problem. And this is all. Thanks very much. Let me show you some references. This paper, the first one. So this work is being accepted in the Journal of Evolution, Equation and Control Theory just yesterday. This is the main paper, the Benelux paper, where we found that's why we call it the Benelux equation. So we put in this name to this equation. And this is one of the main papers of the thesis. With Montes, Alex Montes, we solved the controllability and stabilization of the Benelux equation in the talk. Work by Jones, the Emmanuel Crepeau, Serpa Crepeau. This is it. This is the enhanced theorem with a gut condition. And this is it. Thanks a lot for your attention.
Okay, so thank you very much, Professor Quintero, for this very, very interesting talk, very clear talk also. So we are open for questions. If someone has questions, please raise your hand, and then we will activate your microphone. So maybe Professor Quintero, on the meantime, I have a question, maybe not a technical question, but I became interested recently in control theory and in this controllability of diffusion equations. One of the main tools are Karleman estimates.
Okay.
The question is, how did you to escape in this work, these Karleman estimates that usually are very hard to
well, we don't need to use this Karleman's estimate for this model, but there are problems with these estimates. And with Julio Delgado, we're looking to get Karle's estimates for pseudo differential operators, because there are some results for differential operators. And he told me that the main computation were okay. So I'm really happy with this. We can use this we can use Karle's estimate for different type of problems. For instance, for Benjamin type equations, because we have these symbols which are that doesn't come from differential operator, but comes from for a pseudo differential operator. So like the modulus of C, for example, that appears in the Benjamin-Ono type models. So that's why. But we didn't skip this. Yeah, just we don't need that in this code.
Wow, interesting. Very, very nice. Okay, so any other question?
Not too many, please.
Okay, so maybe we have Tanya. Tanya Verdes, okay. Tanya, you can activate your microphone now.
Hi, congratulations for Professor Quintero for his wonderful results. I just didn't understood why observability and isomorphism are related, because normally isomorphism pops up with 1-1 correspondence of, and then to talk about observability is something that is for every time, for every moment of in a time span. And I would like to have this explanation, because I don't know.
So that's right. That's from here.
Yes.
Here, let's see. Here,
if you
because
please.
this is exactly, this is bound in the observability condition. This thing is bound from above and below for the norm of this guy.
Yes.
Essentially, if this were 0, then you have 0. Essentially, this is an isomorphism. That's the reason for this, right? So this is the key. This is the keystone of the AUM method, the Hilbert uniqueness method. To have this.
Hilbert what? Okay.
Hilbert uniqueness. Hilbert uniqueness method.
Unfortunately, I have heard the first time I have heard about that, about Hilbert uniqueness method, and I will read about it. And thank you so much that I would like to have this all under control. It's very important to have the system under control, because it's a crucial problem for safety and for civil security. And thank you so much for this very important subject to address. Thanks.
Thanks for your question.
So thank you, Tanya. Okay, any other question? Okay, Professor, no more questions. So thank you very much for this amazing talk. I prove that still doing some administrative tasks, you continue working very hard in mathematics.
Thanks for the invitation, and thanks for your generosity. And well, I hope that the talk matches the expectation. But okay, thanks a lot.
Thank you, Professor. So see you in your tribute later.
Okay.
So okay. So when we will have the at 11 in Colombian time, we will have the plenary talk of Professor Donaldson.
Okay.
So see you almost in 1 hour.
Bye. Bye.
Bye-bye.
Ah, pasamos foto, nadie come 2 pan de bono ahí.
Okay. Professor Donaldson, can you hear me?
I hear you, yes.
Okay. Hi. It's a pleasure, Professor. I think we can start now. Nice to meet you, Professor. My name is Brian Grajales. I introduced the organizing committee. It is Duan Cardona, Jessica Gonzalez. If you want, you can share. You already shared your screen. So, I couldn't imagine a better final talk for this event. It is an honor for me to introduce one of the greatest mathematicians in history, Professor Simon Donaldson. Anyone in the world of mathematics has heard about Professor Donaldson. For his contributions in topology and geometry, he has made great advances in mathematics and science in general. It is not surprising that throughout his career, he has been awarded so many times. He was invited speaker at the International Congress of Mathematics in 1983 and plenary speaker in 1986, 1998, and 2018. Among the most outstanding awards are the Junior Whitehead Prize in 1945, Crawford Prize in 1994, Kim Faisal International Prize in 2006, Nemmer Prize in Mathematics in 2008, Breakthrough Prize in Mathematics in 2014, Oswald Veblen Prize in Geometry in 2019, Wolf Prize in Mathematics in 2020. And it is necessary to mention that he was elected Fellow of the Royal Society and received a Fields Medal at the International Congress of Mathematics in Berkeley in 1986. But his work as a mathematician goes beyond science. Let me explain this to you. All the members of the organizing committee of this event had the opportunity to meet Professor Donaldson back in 2012 at the School of Geometry at the University of Valle. Without a doubt, this motivated us to continue our studies and to do mathematics. Situations like this happen every year in all the world's universities. So we are sure that his work has inspired thousands, maybe hundreds of thousands of mathematicians around the world, making his contribution to humanity invaluable. It is an honor for us to listen to you, to your talk today. Welcome, Professor Donaldson, and thanks again to be here.
Well, thank you for the very kind introduction, and thank you for inviting me to give this talk at this important meeting. The title perhaps doesn't give a very clear idea of what the talk is about. What we're going to be talking about are some questions related to an important area in contemporary differential geometry, studying various special structures in what you might call middle dimensions, not too low, but not special things that are specific to things in dimensions around about 6, 7, 8, and so on. So let me begin by giving some background in this area. That will be quite condensed, of course, because there's a lot that one would like to say, which we don't have time for. I'll start off by mentioning some things that many of you will have heard of. These are Calabi-Yau manifolds. These are, from one point of view, very special kinds of Riemannian manifolds. For one thing, they're complex manifolds, so they have even dimension, say 2n. They're remarkable in that they satisfy the Riemannian version of Einstein's equation with no source term. In other words, the Ricci tensor, which is the object that appears in Einstein's equation, is 0. And from another point of view, they have what's it's called holonomy. This is a concept in general and in differential geometry, is contained in the group SUN. It's to say, if we parallel transport tangent vectors around loops, they come back rotated by elements of this group SUN. So in fact, as you'll see, what is be relevant for this talk is what we'll call a complex Calabi-Yau manifold, by which we mean just a complex manifold with a holomorphic volume form. That's to say, in local complex coordinates, suitable local complex coordinates, Z1 up to Zn, this volume form is just the product of dz1 to dzn. So we're not considering in a complex Calabi-Yau manifold for our purposes doesn't come with the Riemannian metric. So there are two other cases known where one can find, say, compact manifolds, for example, with Ricci curvature equal to 0. And these both occur in the situation of manifolds with special holonomy. And rather than forming a general family, as in the case of Calabi-Yau, these are very special to particular dimensions 7 and 8. They're related to various kinds of special algebraic structures, exceptional Lie groups, the Cayley numbers, which is an 8-dimensional non-associative algebra. But we won't have time to say anything really much about that in this talk. But the holonomy groups are, in one case in dimension 7, this exceptional Lie group G2, the other case in dimension 8, what's called spin 7. So related to these special phenomena in dimensions 7 and 8, there are also special features of Calabi-Yau manifolds in real dimension 6. There are constructions and things one can do in this dimension which don't apply for general Calabi-Yau manifolds. So this will form the overall context for the talk today, exploring these kind of special structures in dimensions, in these sort of intermediate dimensions. More specifically, we're going to consider complex Calabi-Yau 3 manifolds, so real dimension 6, and what are called G2 manifolds, these manifolds with holonomy G2 in dimension 7. And we're going to say some things about differential geometry of those structures. So to go back and build up some of the foundations of this, we want to go back to some algebra, and this algebra could be developed in a variety of ways, but the approach we'll take will be based upon exterior algebra. If you have a vector space, we can form its exterior powers. So let's start with the 7-dimensional situation. If we have a 7-dimensional real vector space with an orientation, and supposing we have a 3-form on that, so we have an element in the 3rd exterior power of the dual space, if you like, a totally antisymmetric trilinear map from V to R, from V times V times V to R. Then the special thing we can do is define a quadratic form on V, not initially with a real valued quadratic form, but with values in the line of the top dimensional exterior power, the line of volume forms. So this is defined by, we take a vector in V, then we make the contraction of our 3-form phi with that vector to get a 2-form. We take the wedge product with itself, the square, and then wedge it with phi to get up to dimension 7, to get a 7 form. So although this is not, at least initially, a number, this line, because we have an orientation, there's a well-defined notion of positivity. So it makes sense to say that this quadratic form is positive definite. In that case, we'll say phi is a positive 3 form. So this is clearly an open condition on the 3 forms on our 7-dimensional vector space. And what this gives us, if we have such a form, is a conformal class, initially, of Euclidean structures, because if we choose a volume element, then this thing is a number. But there's a way to fix a scale by requiring that the norm, the square of the norm of phi in the preferred metric is equal to 7. 7 is just a convenient normalization. So the conclusion is that starting with a positive 3 form, we have a way of defining a Euclidean structure on our vector space V. So in particular, we get a volume form. This will be really the crucial thing for the purpose of this talk, and also a 4 form given by the star of phi defined using this Euclidean structure. So this star of phi, this is actually a complicated nonlinear construction because we've used the Euclidean structure defined as in the way we've explained in order to define this star. So if you wrote it out explicitly, this star of phi would be given by a complicated expression in the components of phi. But the crucial thing for us will be the variation of the volume form of phi if we vary phi. So if we consider, for example, a one-parameter family, a smooth path of positive 3 forms, then we get a path of volume forms, and we can differentiate that. And the formula is that this is given by star phi. We take the wedge product of star phi with the derivative of phi. In fact, we could have used this, if we liked, as a way of defining star phi. If we just defined this volume form, then looking at its variation would give another route to defining this 4 form star phi. So there are many things one could say, which we don't really have time to go into much. One is that these positive 3 forms are all, in a sense, the same. More precisely, they're a single orbit under the action of the orientation-preserving linear transformations of V. So it's a similar situation to that of symplectic forms in an even-dimensional vector space, which, of course, are all the same in the same sense. They're all equivalent under linear transformations. Well, you might like to say, well, let's at least see one of these people, one of these objects, and later in the talk, we'll write down an explicit model for a positive 3 form. So, as I said, once you've seen one, you've seen them all, in a certain sense. So if we have a positive 3 form, then we can look at its stabilizer in the group of linear transformations. And this is a compact Lie group, it is in fact isomorphic to the 14-dimensional exceptional Lie group G2. So this is very plausible. Well, just on the naive dimension counting, the space of these linear transformations, that group has got dimension 49, whereas the space of these 3 forms has got dimension 35. So the plausible picture is that we have an open orbit and the stabilizer is dimension 14. And that turns out to be the case. So that's the relevant algebra in dimension 7. Let's now do the corresponding thing in dimension 6. So let's W be an oriented 6-dimensional real vector space, and again take a 3-form on W. What can we do now with this? What we can do is define a map from W to the 5th exterior power of the dual, defined by taking, for any vector W, little w, in the vector space W, we take the contraction of rho with W, and then take the wedge product with rho to get up to the 5th exterior power. Now, a basic fact of exterior algebra is that the 5th exterior power of W star is isomorphic canonically to W tensored with a 1-dimensional vector space, the top exterior, the space of volume forms. So our linear map we've defined is a map from W to W tensored L. So in this situation, we can define the determinant of this map. If we just had a map from W to W, of course, the determinant will be a number. Because of this line we're tensoring with, the determinant lies in the 6th tensor power of this line, if you like. But since these are real lines, we can take roots, and we can define again a volume form by taking the 1/6 power of this determinant. So the conclusion is that if we have a 3-form on a 6-dimensional vector space with an orientation, we get that determines a volume form. So again, we can look at the derivative of this volume form with respect to the variation of the 3-form, and this produces another 3-form by this formula. So we have a formula, we have another 3-form, a sort of a companion rho tilde. So the variation of the volume form is given by the wedge product of rho tilde with the variation of rho. All very much parallel to what we did in 7 dimensions. So again, one finds that there is an orbit of positive three forms, which all have stabilizer isomorphic to SL3C, the complex group of 3x3 matrices of determinant 1. So again, this is plausible by sort of a naive dimension counting. So such a 3-form, one of these positive 3-forms, defines a complex structure on the real vector space W, and the complex 3-form we get by taking a combination of rho and rho tilde is equivalent to the model form that we talked about before on C3. So a positive 3-form rho is just one which is equivalent under linear transformations to the real part of the standard form dz1, dz2, dz3. So we could, if we had a few more minutes, we could explain how one defines a complex structure from a 3-form, but we won't, we'll omit that for shortage of time. It's a similar kind of, somewhat similar to what we did in defining the Euclidean structure in the 7-dimensional case. So that's our algebraic background. Special things we can do with exterior algebra in dimensions 6 and 7. Let's now go over to differential geometry and use these ideas on manifolds of those dimensions. So starting in 7 dimensions, if we have an oriented 7 manifold and we consider a 3-form on it, then it makes sense to consider a 3-form which is positive at each point. Such a thing defines a Riemannian metric. As by applying the algebraic constructions we made in each tangent space, it defines a 4-form and a volume form. So all of this is just algebra in the tangent spaces of our 7 manifolds. But then there's a remarkable characterization of these torsion-free G2 structures we talked about, just in terms of this data. So this is a result of Fernandez and Gray, one of the early results on these G2 structures. Giving one of these structures is equivalent to giving a positive 3-form, as above, which is closed, d phi is 0, and so that the 4-form, star phi, is also closed. So if you like, you don't need to know anything about holonomy or G2 or all these other things, because you could define one of these structures just to consist of a form satisfying these equations. Similarly, in 6 dimensions, if we have a 3-form, then which is positive at each point, it defines a companion 3-form, rho tilde, and a volume form, and it's a similar fact in differential geometry that a complex Calabi-Yau structure is equivalent to giving a rho such that rho is closed and its companion rho tilde is also closed. These equations imply the integrability of the almost complex structure that one has on the manifold. So there's a beautiful variational point of view on this due to Hitchin. Let's suppose we have our 7-dimensional manifold, a closed manifold, a compact manifold without boundary, and fix a cohomology class in the 3-dimensional cohomology. So then we can look at the positive 3-forms in this cohomology class. That's to say, the closed positive 3-forms in that de Rham cohomology class. So varying in this set, remember if we take some initial value, initial phi, varying in this set, we're only allowed to vary by the derivative of a 2-form. Of course, this set might be empty. We might have a cohomology class where there is no positive 3-form representing it. But let's suppose that's not the case. Then we can consider a volume functional on that set, just given by integrating the pointwise volume form that we've defined. So this is a functional of a phi in this cohomology class. So as such, we get Euler-Lagrange equations, which are given by the condition that the first variation of the functional is 0. So what are those? If we consider a path where we change some reference phi by adding d of a 2-form, then we have to differentiate the volume form. So that's given by taking, remember, the derivative of phi, which is just d of the derivative of sigma, and wedging that with the 4-form. So now we can integrate by parts, that's to say, apply Stokes' theorem, and write that as the integral of the derivative of the 2-form by d of star phi So this vanishes for all variations if and only if d of star phi is 0. So what we conclude is that the critical points of this Hitchin functional are exactly the torsion-free G2 structures in the given cohomology class. And there's an exactly parallel discussion in the other case, in the 6-dimensional case. A positive 3 form defines a volume at each point. We can integrate that to get a volume functional, and in just the same way, the Euler-Lagrange equations associated to that are the equations for structures which define complex Calabi-Yau structures. So everything I've said so far is sort of general background in this area. Let's move on to the more specific topic of this talk, which is to consider boundary value problems for these kind of differential geometric structures. On this variational point of view, it motivates what the right boundary value problem to consider should be. If now we have a compact 7-dimensional manifold with boundary and fix a closed 3 form on the boundary, then we can consider closed positive forms on the manifold which restrict to chi on the boundary. Now, more precisely, we want to fix a cohomology class. So more precisely, we're taking one form, we take some reference form which restricts to phi on the boundary, and then we're only allowed to change it by d of sigma, where sigma vanishes on the boundary. So again, we have a volume functional on this space of 3 forms, and the critical points are exactly the torsion-free G2 structures with boundary value the prescribed form chi. That's to say, if we go back to this manipulation, if we're doing this on a manifold with boundary in general, when we do this integration by parts, we would get a boundary term, but that will involve the variation of sigma on the boundary, which we're requiring to be 0. So this boundary value problem, looking for a torsion-free G2 structure which restricts to a prescribed closed 3 form on the boundary, is the natural one to consider from this variational point of view. And again, we can say essentially exactly the same thing in the 6-dimensional case, studying complex Calabi-Yau structures with a given real 3 form on the boundary. Well, you might be thinking that I'm now going to tell you lots of big theorems about this problem, this question of solving this kind of boundary value problem for these structures. That's not really the case. This is a new area. In general, in this field of exceptional holonomy, our ignorance is much greater than our knowledge. Most questions that one can ask, and most obvious questions, the answer is not known. But there are various things that we can say, and I want to tell you about. The one is, so the most basic thing to look at if we have a differential geometric problem is to understand the linearization, either the deformation theory. Now in this 7-dimensional case, one can set it up as an elliptic boundary value problem. So more precisely, this is when we work modulo diffeomorphisms of the manifold, fixing the boundary. So there's a deformation theory of a sort of familiar kind. There's possibly in some cases a a finite dimensional obstruction space for deformations, but at least in many cases of interest, this can be shown to be zero. And if that is the case, if we have a solution for one boundary value, then it can be deformed to a solution for any nearby boundary value, and moreover, uniquely. So for this kind of a good existence and uniqueness theory for small deformations about a given solution. So again, in general, in these differential geometry, what one would like to do alongside that would be to derive estimates on the solution, sort of a priori estimates, which one would allow one to consider large deformations of the boundary value, i.e. to apply kind of a continuity method to prove general existence theorems. So we would like to be able to estimate various quantities of a solution of this structure on M in terms of the boundary data. And there are various interesting things in that direction. But let's just mention one thing. There's one simple way in which an existence, an optimistic existence conjecture could fail by the phenomena that you could have solutions where two parts of the boundary come together. So you have a picture looking something like this. You could think of it, for example, just as a domain in Euclidean space. The structure on the boundary here is perfectly nice, no kind of singularities, but the domain sort of becomes singular because these two bits hope for general existence theorems, it's natural to look for kind of convexity hypotheses, which can rule out this kind of boundary touching behavior. So there is such a hypothesis that one can make. So let's see, if we took just an algebraic condition, if we're to have one of these positive forms phi on the 7 manifold with the given boundary value, just a rather obvious algebraic condition is that chi itself is positive. So chi defines, our boundary data defines an almost complex structure on the boundary of the manifold, and also a companion 3 form, chi tilde. So on an almost complex manifold, there's a notion of positivity for 4 forms. That's to say, if we say a 4 form S is positive, is if we take the wedge product with eta, wedge eta bar, where eta is a 1,0 form, and then multiply by I, the square root of -1, then that thing should be positive. So that means that we can take our chi tilde, we can take the exterior derivative to get a 4 form, and then it makes sense to say that that 4 form is positive. And so we'll call such a structure mean convex. Then one can show by some very simple differential geometry that if this condition is satisfied, if our boundary data is mean convex, and if we found a solution phi on our 7 manifold N, then the boundary has positive mean curvature inside the Riemannian manifold M. So this prevents this kind of boundary touching behavior, because you can't have 2 pieces of boundary coming together if they both have positive mean curvature with respect to the outward normal. So a kind of a sample question, one might ask, or at least a plausible question, would be that if we have a path of these mean convex closed forms on the 6th sphere, deforming the standard structure, can we find a path of solutions to our G2 equations, the three forms on the 7 ball, which deform the flat structure on the ball? So we start off with the sort of trivial solution just by the flat structure, the flat metric on the 7 ball. We start deforming our boundary data within the class of these mean convex forms. Can we keep on deforming our solution phi? Or do we develop some other kind of singularities, or do other bad things happen? So I say questions like this and this kind of generality are really out of reach at our present state of knowledge. But I should say that this kind of questions is, at least to me, is one motivation for studying this boundary value version of the theory, in that if we look at known examples of compact manifolds with these torsion-free G2 structures, they're all very complicated manifolds with second Betti number typically, with Betti numbers typically around about 100 or so. So they're difficult things to think about. So it's, to me, it's appealing that one can ask these questions for these boundary value problems just working with very simple manifolds. So, I said, these problems in this generality are difficult. Will probably be many years till they can really be addressed in generality. But they become simpler if, in the standard fashion, one looks at dimensional reductions by imposing symmetry to get problems in lower dimensions. So somehow the main point of the second part of this talk will be to show you two of these dimensional reductions which lead to interesting questions with familiar geometric data, we could say. So let's discuss some of these reductions in the 7-dimensional case. So here comes our promised model for a positive 3 form. There are various ways of writing down a standard model, but we'll use this one. If we, let's start with R4, thought of as having its Euclidean structure and an orientation. And then the thing we can do there is to decompose the 2 forms into the self-dual and anti-self-dual parts. So if you recall, if we take coordinates x0 up to x3 on R4, then the standard basis for the self-dual forms can be taken by taking dx0, dxi, plus dxj, dxk, where ijk run over cyclic permutations of 1, 2, 3. So we've got 3 standard self-dual forms in this way. So now if we think about R7 as R4 times R3, we can write down a 3 form by taking coordinates T1, T2, and T3 on R3. We take the product of the dt's, and then we take this combination of the self-dual 2 forms on R4, with the dti. You see, indeed, there are, if we wrote this out, there are sort of 7 monomials in this expression, because each of these is, there are 3 terms here, and they each involve these 2 terms. So this indeed is normalized in our standard setup to have the square of the norm is equal to 7. So there are 7 terms, 7 monomials, if one writes this out. So now let's take a 4 manifold and take a triple of closed 2 forms, such that the matrix we get by taking the wedge products between them is positive definite. So again, this is a bit like what we had before. This wedge product is a 4 form, so it's not immediately a number, but because we have an orientation, it makes sense to say that this thing is positive definite. And we can take any volume form to interpret this as a number, and that will give the same notion of positive definiteness. So now, in terms of this triple of closed two forms of a four manifold, we can write down a positive three form on the product of the four manifold with R3. Just using the same, what's the same expression we wrote down before. So this gives one interesting reduction to an equation in 4 dimensions for a triple of closed two forms, which we can write out. But we won't do that here. We'll go on to do a further reduction by requiring that there's a circle action on our four manifold, a free circle action generated by a vector field, V, and we look for solutions which are invariant under this circle action. So starting in 7 dimensions, we're looking at solutions that are invariant under 3 translations and then this circle action. So we have 4 different symmetries. So what can we do? So the hypothesis means that the omega 1, omega 2, and omega 3 are symplectic forms on our 4 manifolds. So under natural hypotheses, we have Hamiltonian functions in the usual way corresponding to this vector field V, because the action is supposed to preserve these forms omega I. So we can put these together to give a map from X to R3, which we'll suppose has image some bounded domain U in R3. So now we get a problem that we can set up on R3, in fact on this domain U in R3. So setting it up takes a bit of time and going through the equations and various transformations and so on. So I'm just going to tell you the conclusion of what you get when you do that. So we have our domain U in R3, which you might want to think of this as a convex domain with a smooth boundary. And what happens is that the boundary data that we have in our problem coming from our differential forms, turns out it defines 2 things. It defines an area form on this boundary, and also it might call a normal vector field, at least a vector field transverse to U. So at each point of U, we have a vector in R3, which is transverse to the tangent space of U. So what this does, it defines a linear functional acting on functions, well, you could think, for our purposes, acting on functions on U, but it really only involving functions on an infinitesimal neighborhood of the boundary of U, given by integrating, with respect to this area form, the sum of the normal derivative and the function. So the sort of PDE analysis problem then, which is equivalent to our boundary value problem, is one of an interesting kind, which seems to be quite natural. I'm not aware that it's arisen anywhere else, but anyway, it seems quite interesting. So the problem is we look at all solutions of the Monge-Ampère equation. We look at convex functions f, the determinant of the Hessian is equal to 1 on our domain U, and then we want to minimize this functional L of f over that set. So this is really depending on just on the boundary value of f and on the normal derivative. So this is, I think, an interesting kind of analysis problem that one probably can say quite a lot about. And is, say, a special case of this in this dimension reduction version of the complicated problem we started with in 7 dimensions. Okay, so now in my lastly we'll go to the 6-dimensional case and say something about that. Although what I'm going to say here is this is joint work with my colleague Fabian Lehmann in the Simons Center in Stony Brook. So as in the title of this talk, what we're going to get here is really a mapping problem rather than being explicitly a boundary value problem. An important difference between the 2 cases that we're discussing, the complex Calabi-Yau structures and these G2 structures, is that the complex Calabi-Yau structures are locally trivial. We can always choose complex coordinates in neighborhood of a point, and the 3 form is just the standard form dz1, dz2, dz3. There are no local invariants. Whereas in the G2 case, we get a Riemannian metric, for example, and so there are lots of local invariants. So supposing we're considering our boundary value problem in the setting where we have one solution which is what's called a domain in C3 satisfying the condition of being pseudo-convex, which is a well-known thing in several complex variables. So it's a variant of the usual notion of convexity. Then it's a fact proved by Hamilton that any small deformation of Z, just as an abstract complex manifold, is still a domain in C3. The only way you can deform Z is by deforming the domain in C3. So if we're studying our boundary value problem in the context of these kind of manifolds, it becomes equivalent to a mapping problem, at least the deformation version. So how does that mapping problem go? Let's have a compact 5 manifold, let's call it N, and supposing we're given a closed 3 form on N. So the question is, can we find an embedding of N in C3 so that the pullback of the real part of our standard 3 form, dz1, dz2, dz3, is the given form psi? Well, you can think of this as the pullback, but if you think of this as an inclusion, you could think of this also as the restriction of rho naught to N. So N will be the boundary of a domain in C3. And that will be the tie-up with our previous point of view. So this is a question that we can consider. But of course, it wouldn't. I mean, we couldn't if we started with the form 0, psi equal to 0, for example. There wouldn't be a sensible question. Obviously, it's impossible. So to make a sensible question, a more focused question, we need to understand something about the structure theory of closed 3 forms in 5 dimensions. We talked about the structure theory in 6 dimensions and 7 dimensions. Now we want to say something in the same vein in 5 dimensions. And this is quite interesting. So what can we go back to some just sort of algebra initially? If we have a 3 form on a 5-dimensional vector space, either tangent space or manifold N, it defines a skew-symmetric form on the dual with values again in the top exterior power by just taking so there should be some brackets here. We take a pair of elements of cotangent vectors, take their wedge product, and then wedge them with psi. So remember that a skew-symmetric form on an odd-dimensional vector space is always degenerate. It can't have maximal rank. So, well, so the maximal rank it can have is 4 rather than 5. So our first assumption we're going to make is that our given form does have that maximal rank at each point. That means we can write psi as the wedge product with a 1 form theta and a 2 form alpha, and we get a rank for subspace at each point, the kernel of theta, inside our tangent space. In other words, we get a rank for subbundle inside the tangent bundle of n. So our next assumption is that this subbundle is what's called a contact structure on n, which it means that if we write, we take the exterior derivative of this 1 form theta, then the wedge product of theta with the square of that exterior derivative is a volume form. This is a way of expressing the definition of a contact structure. So we have something else we can do, which is to take the wedge product of alpha. We can take the square of alpha and wedge that with theta to again get a 5 form. So these things differ by a function f. Then our final assumption is that this function f is positive. So we'll call a closed 3 form satisfying those assumptions pseudo-convex. Notice these are all open conditions, so we have an open set of closed 3 forms on a 5 manifold. And this terminology is very reasonable because it's easy to see that if we do have, if n is the boundary of a pseudo-convex domain, then the restriction of our basic 3-form rho naught on C3 is pseudo-convex on n in the sense we've defined. So the main result with Fabian is that we have a formation theory in this situation with a similar conclusion to that we enunciated in the 7-dimensional case. So there's possibly an obstruction space, an obstruction to deforming a 5-dimensional vector space, but that can be shown to be 0 in many cases of interest. And when it's 0, then you have existence and uniqueness for the problem, for the deformation problem. So for example, to give a concrete example, if we take the standard 3 form on the 5 sphere, given by the standard 5 sphere in the C3, any small deformation of that is realized by a small deformation of the embedding of the 5 sphere in C3. And this is unique up to holomorphic volume-preserving diffeomorphisms of the interior. Obviously, if you have one embedding, bounding a domain, if you have a holomorphic volume-preserving diffeomorphism taking that domain to another domain, smooth up to the boundary, then that gives you another solution. So up to that obvious fact, we have uniqueness. So I'm not attempting to say anything about the details of this, that while the results in the end, the conclusions are much the same as in the 7-dimensional case, there are important differences, is that this is not an elliptic PDE problem. So one can't use the relatively standard kind of elliptic theory and implicit function theorem and Banach space techniques, but one can obtain subelliptic estimates, kind of half estimates, which give some control of the linearized problem, and then apply the Nash-Moser implicit function theorem to solve the nonlinear problem. Now the fact that one has these subelliptic estimates depends crucially on the pseudo-convexity hypothesis, much as in the well-known theory of CR structures in complex variables. So again, a sample, ambitious, out-of-reach question, but interesting, could have a positive answer, is can any pseudo-convex free-form on the 5-sphere be realized by an embedding in C3? If we start off making small deformations from the standard solution, we know it can be. What happens if we try to go a long way? Can we keep on going? Do we develop some kind of singularities or other bad behavior? So finally, let's again talk about a dimensional reduction. So this is going to, of this 6-dimensional problem, but this is going to lead to not a question which is, as far as I know, new, as in the case of the Monge pair setup we discussed, but a very old and famous problem in differential geometry. So this is what's called the Minkowski problem. So just to recall first what that is, in understand the formulation, is if you take the standard sphere in R3 and a given positive function k on it, can we find a surface in R3 so that the Gauss curvature of this surface at a point is given by the value of k at the normal direction at this point. See, the normal nu of p is a point in the 2-sphere, so we have a value of the function k there. So it's the problem of prescribing the Gauss curvature as a function of the normal direction. And this is, I believe, important in both in differential geometry, but also in diffraction theory and other things of that kind. So anyway, this was a famous problem solved by Nirenberg and independently by Pogorelov back in the 1950s. And it's part of an enormous area, which include the result proved by Nirenberg and Pogorelov is that there is indeed a solution, provided K satisfies some obvious integral conditions that Pat will write down later. There is a solution, and it's unique up to translations. Obviously, we could translate S in R3. That would give another solution. So what does this have to do with our problems in these high-dimensional geometry? Let's now consider a two-manifold, sigma, a compact-oriented two-manifold, and a triple of two forms on sigma. So it's a bit in the vein of what we were doing before, the triple of two forms on a four-manifold. And we assume they don't simultaneously vanish. There's no point where they all vanish. So if we have this triple of two forms, again, we can write down a 3-form now on sigma times R3. So again, similar in spirit to what we did before. And so we want to consider this sort of dimensionally reduced version of our problem. That's to say, we want to consider embeddings of sigma times R3 into C3, which are really defined by an embedding of sigma in R3, thinking of R3 sitting in the standard way as the real part of C3. And then we're just mapping the R3 into the imaginary directions in C3 in a sort of trivial way. So we can ask our general problem for this special class of three forms on this 5 manifold and these translation invariant solutions. So you need to spend a little time to think about this to get clear, but we can write, if we put these three two forms together to give an R3 valued two form, then the fact that these things don't all simultaneously vanish means we can write that as the product of an ordinary two form, an area form on sigma, and a map from sigma to S2. Now, think for a moment, you'll see that that's possible in a unique way. So a little calculation shows that our pseudo-convexity hypothesis is equivalent to saying that the map from sigma to S2 is a local diffeomorphism, oriented diffeomorphism locally. But since S2 is simply connected, it must be a global diffeomorphism. So we can define a positive function k on the two-sphere, determined entirely by our original data, this triple lambda 1, lambda 2, lambda 3, given by comparing the form omega with the area form A under this diffeomorphism L. Then it's an elementary exercise, but it may take a bit of time, a little bit of thought, to see that our embedding problem for the map F is exactly equivalent to the Minkowski problem with this function k determined by lambda 1, lambda 2, and lambda 3. So in this case, by applying the result of Nirenberg and Pogorelov, we do get a decisive general existence theorem for this dimensionally reduced version is just that the integral over sigma of these lambdas should be equal to 0. Well, my time is up. I say this is a relatively new area. Not much is known in general, but I think it will be a lot of scope for work in the future. And the fact that there are these connections with interesting problems in these more down-to-earth, low-dimensional situations seems to me to give evidence for the interest of the general setup. Thank you very much for your attention.
Thank you very much, Professor Donaldson. So now we are open for questions. If someone has a question, please just raise the hand. Okay, Ji-Hun Lee.
Yes, first of all, thank you very much for your lecture, Professor Donaldson. I'm Gi-Hun Lee from Korea, currently working in Belgium. So my question is for the elliptic boundary value problems arose in your study. Can we get any useful conclusion if one applies the theory of pseudo-differential operators to such elliptic boundary value problems?
I'm trying to think of an answer. I guess those pseudo-differential operators are very relevant to the linear aspects of the setup. For example, in particular, in applying this more sophisticated theory where one was in the subelliptic case, so you have a non-coercive boundary value problems, and so
yes.
the theory is very relevant there for the linearized version. It's not, as far as I know, I don't see a direct relevance to the kind of non-linear questions of how you obtain estimates, geometric estimates for solutions. But
Okay.
could well be. Yeah.
Okay.
Right.
Thank you, Jishmu. So, David Santiago Gomez, you can activate your microphone, Santiago.
Okay. Thank you very much, Professor, for your nice talk. I'm also a student of Professor Rusanski here in Belgium, and I would like to know if you can talk maybe more about the finite dimensional vector spaces that you mentioned that are abstraction to the solutions of the equations. Are somehow the dimension of those spaces like the index of an operator somehow, and that's why you get 0 dimension?
I don't think they're exactly, no, they're not exactly the index. They are mysterious. There are sort of reasons for thinking they might always be 0. Or in fact, I've spent quite a lot of time trying to prove that in the two contexts, but without complete success. So they are mysterious. It's related to the question of uniqueness. If you had a case where you had this non-trivial abstraction space, you'd expect that for nearby data you had two solutions coming together, would be the typical phenomenon. So if they exist, you'd expect also that uniqueness should fail, for example. But it is they are mysterious to me, and it's a very interesting question to study in the future.
Thank you.
Thank you. Thank you, Santiago, for your question. Any other question for Professor Donaldson? Maybe I have a question, but myself in this very famous problem that you mentioned, the Minkowski problem, about for given a positive function k to find one surface with Gauss curvature equal to k. My question is how much regular the function k is, if the function k could be Lipschitz, or how regular is the function k?
Well, okay, I'm thinking entirely in the smooth situation.
Okay. Okay.
But
Thank you.
I guess it definitely is, and I can see it would definitely be interesting to extend the theory to more general functions k, because of course if you have a domain, you're talking about a convex set essentially, so it's very natural to consider non-smooth convex sets.
Okay.
So I imagine there probably is some literature about that, but and it could also be interesting in our context too, of where one might want to work with things not with smooth boundary, but more general. But that will have to be for the future. I haven't thought, so far I've only thought about smooth situations.
Okay, thank you very much. So any other question for Professor Donaldson? So, Tanya, you have a question. So, Tanya, you can unmute by yourself. Tanya, we can hear you.
Yeah, hi,
okay,
hi. I have a small son, and I would like him to understand quantum physics and quantum chemistry. And I would like to ask you what would be the starting point for understand quantum physics for school children, and relation with mathematics. And also I would like to ask you about pseudo convexity. Do you have some second derivative and court definition for the pseudo convexity? Analytic and synthetic approach.
Right. So your first question about quantum physics, I'm not the person to answer. I mean, I would really like to know the answer. I have a big stack of books about quantum physics and quantum field theory. Of course, I have many colleagues who are experts in such things, but I've only managed to absorb the most amateurish sort of knowledge myself. So I don't think I could give really helpful advice about that. Your second question was
for
about,
example, once yes, I try to understand why electrons are the force between two particles of same charge is that they go they attract each other. They do not attract each other, and from the opposite side they attract each other. You know, a force exists, and I tried to find out the rigorous explanation to that, and there is no explanation, just quantum field theory, and there are virtual particles include. And what would you feel? What would be the solution for this virtual introduction of virtual particles, virtual methods or objects or categories, just to fill the gaps of what we do not yet model with mathematics?
yeah, I don't think I can really have anything useful to. I agree. It is difficult to bridge the language gap between the physics literature and mathematics, but I don't think I can say anything that's a very helpful technical level. Yeah, I think you did also ask about pseudo-convexity.
Yes, I would like to have the. Do you have a publication where you introduce the scientific and analytic part of like second derivative and a chord for pseudo-convexity?
Yeah, well,
or something like.
Let's explain. If you have a complex, well, then in a complex manifold, or just in Cn, you have what's called the d bar d operator, where you take the second. So more or less pseudo-convexity. If you take ordinary convexity, that can be expressed in terms of the Hessian of a function, taking the second derivative. So
Exactly. Yes.
Or
something it should be. Yes. Or a line should be always below the curve, and so on. Something like that.
Yes.
Okay, thank you, Tanya, for your question. Okay, if no more question, thank you very much, Professor Donaldson, for accepting our invitation. Always in the Universidad del Valle, you are welcome, and in our events and conferences. Thank you very much.
It's my pleasure. Thank you.
Okay, so maybe Jessica, you can inform something about the tribute to Professor Quintero.
20 minutes, we will start the tribute that we will do to our teacher, our professor in Valle University. So wait for us only 20 minutes and we'll be here. So we will start the tribute to the Professor Quintero. So I invite you to open your screen for your camera for some of you that you can do, if you can do it, please.
Okay. So, Professor Quintero, thank you for accepting our invitation. Now we will present a video about the academic life of Professor José Raúl Quintero, to whom we dedicate this conference.
José Raúl Quintero Henao nació en Bugavalle el 12 de noviembre de 1960. Es el hijo mayor de la señora Cándida Rosa Henao. José Raúl tiene 3 hermanas, Gladys, Zoraidi y Edith. Siempre guardó admiración y un profundo respeto por su familia y especialmente por su madre, Cándida Rosa, quien siempre estuvo comprometida con la formación académica y el desarrollo personal de sus hijos. De ella recibió orientación y un apoyo incondicional en cada etapa de su vida. En sus estudios universitarios, su tío Gustavo Henao y su esposa Gloria Estrada fueron fundamentales. Su familia, su hijo Raúl Eduardo, su nieta María Isabel y su esposa Erika Cruz siguen siendo el pilar principal de su vida. Quintero estudió en el Colegio Académico de Buga, uno de los mejores colegios públicos del municipio, e inició sus estudios de matemáticas en la Universidad del Valle, Cali, Colombia, obteniendo su título como matemático en 1984. Su dedicación y el gusto por esta disciplina lo llevaron a iniciar una maestría en la misma universidad, alcanzando el título de maestro en matemáticas en 1988. Ya para 1990 ingresó a la carrera docente como profesor asociado del Departamento de Matemáticas de la Universidad del Valle y desde 1993 es profesor titular de la misma. Su ánimo y entusiasmo de querer lograr más como matemático y como investigador lo llevaron a obtener el título de doctor en matemáticas en la Universidad de Maryland College Park, Estados Unidos, bajo la dirección del profesor Bob Pego en 1999. Sus intereses de investigación están relacionados con las ecuaciones diferenciales parciales, el análisis funcional no lineal, la teoría de control, la física matemática y los modelos dispersivos no lineales relacionados con ondas de agua, estudiando la buena posición en diferentes dominios, la existencia de soluciones especiales que se pueden presentar como ondas viajeras u ondas estacionarias y el análisis de estabilidad. Hoy en día, el profesor Quintero es decano de la Facultad de Ciencias Naturales y Exactas de la Universidad del Valle, donde ha sido vicedecano de investigaciones y director del posgrado en Ciencias Matemáticas. Aquí su papel fue fundamental, pues impulsó el nacimiento del doctorado en Ciencias Matemáticas del departamento, y tiempo después fue galardonado como profesor distinguido. En el año 2011 conquistó el Premio Nacional de Matemáticas, y 4 años más tarde fue incluido como miembro de la Academia Colombiana de Ciencias Naturales y Exactas. Actualmente es también director del Grupo de Investigación Ecuaciones Diferenciales Parciales y Geometría, EDPG, donde ha liderado varios proyectos de investigación. El profesor Quintero ha dirigido a estudiantes de pregrado, maestría y doctorado. Cuenta con un número importante de artículos de investigación en destacadas revistas científicas de matemáticas a nivel internacional y sigue investigando a pesar de sus múltiples compromisos con la decanatura. Por su gran recorrido académico e investigativo y también por su entusiasmo para querer compartir sus conocimientos, hoy rendimos este merecido homenaje al profesor José Raúl Quintero.
Raúl, felicitaciones por este merecido homenaje. Gracias por tu vocación de servicio y por ser motivo de inspiración para muchos de tus estudiantes. Gracias por tu amistad incondicional y por haberme permitido compartir contigo tantas vivencias, tanto profesionales como personales. Vienen a mi mente nuestras conversaciones académicas en centros como Cornell, Maryland y el INPA, como también momentos de recarga en el Pan de Azúcar, Machu Picchu y las cataratas del Niágara. Con tu creatividad y trabajo cosecharás muchos más éxitos y tendrás más homenajes como este. Un abrazo fraterno.
Bueno, para mí hablar de José Raúl Quintero es como hablar de un hermano. Nos conocemos hace muchos años, desde cuando comenzamos a estudiar en la Universidad del Valle, pregrado, y luego hicimos la maestría juntos. Es un verdadero placer para mí dedicar unas palabras a José Raúl, una persona que merece todos los calificativos, todas las conmemoraciones que se le puedan hacer por todo su compromiso, por toda su dedicación a la matemática colombiana y a la matemática de la Universidad del Valle. Muchas felicidades, Raúl.
Estimado profesor José Raúl, me uno a este merecido homenaje desde Popayán, desde la Universidad del Cauca. De mi parte solo palabras de admiración y agradecimiento. Admiración por esa brillante carrera docente, investigativa y administrativa que ha tenido, por impulsar el desarrollo de la matemática desde la docencia, desde el ejemplo investigativo y desde esa gestión administrativa que ha desarrollado desde la dirección de los posgrados y ahora desde la decanatura. Agradecimiento por ser mi maestro, por ser mi mentor, por haberme acogido bajo su tutela académica cuando llegué a la costa y nadie me conocía. Muchas gracias por mostrarme ese panorama bonito de las ecuaciones diferenciales y el análisis. Muchas gracias por todo, profesor José Raúl. Un abrazo, muchos éxitos en todo lo que viene y muchas felicitaciones.
Gracias a los organizadores del ICMAM 2022 por realizar este gran evento en honor a mi esposo José Raúl Quintero Henao. José Raúl es un gran ser humano con mucha calidez, dedicado a su familia, dedicado a su trabajo, el cual disfruta mucho. Es un gran profesor, un gran investigador, siempre desde su posición como profesor o cuando ocupa un cargo administrativo, busca el bienestar de los estudiantes. A nivel familiar es igual, es un excelente esposo, excelente padre, hijo, hermano, tío y amigo. Siempre da lo mejor de sí y transmite esa alegría que a todos nos gusta muchísimo. José, mereces siempre lo mejor, te amamos mucho, Emma y Erika.
Okay, so thank you very much to all the participants for connecting. Now we will continue this conference, this tribute in Spanish. So, entonces, profesor José Raúl Quintero, este ha sido un merecido tributo a su carrera. Aquí el profesor Marlio Paredes quiere dedicarle algunas palabras. Entonces, adelante, profesor Marlio.
Hola, Duan. Buenas tardes a todos. ¿Me escuchan? Bueno, no, pues me has dicho que era para clausurar el evento. Ya le dediqué mis palabras a Raúl y una vez más, pues muchas gracias por todo, José Raúl, por todos estos años dedicados a la matemática colombiana, a la Universidad del Valle. a tus estudiantes, a los que has influenciado muy positivamente. De verdad que no me alcanzan las palabras para expresar todo lo que pienso, y todos los que te conocemos, pues sabemos que es así. Aquí hay varios estudiantes o exalumnos tuyos y ellos dan fe de eso. Y nosotros como compañeros tuyos, pues también damos fe de toda tu calidad como persona, como profesor, y muchas gracias, de verdad. No sé si quieras, Duan, bueno, ahora más rato hablamos entonces porque para clausurar el evento, ¿verdad?
Sí, muy bien. Entonces, bueno, esta iniciativa comenzó con amigos de la Universidad del Valle y tiene que mantenerse, bueno, quizá incorporando generaciones nuevas de egresados del Departamento de Matemáticas. Entonces, para mí es, bueno, un honor decirles que desde ahora mismo anunciamos una versión venidera del ICMAM 2024. Entonces, por aquí hay una página preliminar y bueno, yo he estado a cargo de gran parte de la organización de esta conferencia y he contado con un equipo gigantesco, un grupo de amigos increíble que bueno, han hecho todo esto posible. Y bueno, de alguna forma, yo quisiera proponer a algunas personas para la organización en el futuro, personas que pueden de alguna forma innovar esta conferencia. Entonces, esta es una página preliminar y bueno, en vista de la participación que deben tener las mujeres en las matemáticas, la presidente de ese nuevo evento va a ser pues nuestra cofundadora, Karina Navarro González. El vicepresidente va a ser Milton Manuel Aguirre. Jessica va a ser nuestra secretaria y si María Alejandra Ramírez Luna acepta incorporarse al comité organizador, pues bienvenida a ser parte de esta iniciativa. Entonces, ya sabremos cómo organizar nuestro evento para el futuro. Queremos, sobre todo, estamos comprometidos con el hecho de que las mujeres en las matemáticas se vean bien representadas y bueno, estas mujeres que ven allí, cada una representa una generación diferente de nuestra comunidad unibayuna y seguro que van a traer muy buenas ideas para esta conferencia. Entonces, bueno, estaremos en contacto con cada una de estas personas. Este es el comité organizador que propongo para el futuro y quiero, bueno, desearles un buen resto de día. Muchas gracias. Profesor Marlio, si quieres continuar.
No, solo darle las gracias a todos ustedes, muchachos, de verdad que es un orgullo que el departamento tenga tan egresados como ustedes con este tipo de iniciativas tan importantes. Muchísimas gracias, porque no solamente es bueno para ustedes, sino para nosotros como Departamento de Matemáticas, para el posgrado en Ciencias Matemáticas y para la universidad en general. Muchísimas gracias, de verdad. Muy interesante todo, muy agradable ver al profesor Donaldson aquí después de muchos años. Lo conocí en el 86 cuando recibió la medalla Fields, estuvo en Cali y fue algo muy interesante. Bueno, ahora hablaba con Brian, él no sabía eso, pero bueno, de verdad muy agradecidos por todo. Quizás sea bueno, Duan, que le des la palabra a Raúl, y no solamente porque es el homenajeado, sino porque es el decano de nuestra facultad.
Imagínese lo que sucede cuando los nervios lo atacan a uno. Profesor Raúl, por favor.
¿Me escuchan? Sí.
Sí, claro que sí. Qué bueno verte.
Bueno, muy buenas tardes a todos. Infinitas gracias al comité organizador, a todos los participantes por semejante homenaje. Realmente es una muestra de cariño y pues de reconocimiento a un trabajo, pero digamos un trabajo que nació en la Universidad del Valle. Realmente la Universidad del Valle es digamos, es la promotora de todo esto que estamos haciendo. Todo lo que he hecho se lo debo a la Universidad del Valle y yo he sido fiel a eso. O sea, en cierto sentido, pues lo que hacemos nosotros como profesores es retribuir, ¿cierto? Todo lo que la universidad nos ha dado, todo lo que el país nos ha dado. Y cuando uno revisa, digamos, hace un análisis de los egresados, pues se encuentra que tenemos un talento enorme en la Universidad del Valle, muchachos que están en distintas partes del mundo haciendo un trabajo espectacular, que han pasado por nuestros salones de clase, algunos han pasado, otros no, pero de alguna manera, digamos, están llevando el nombre de la Universidad del Valle y el Departamento de Matemática a unos niveles internacionales muy importantes. Lo único que yo he hecho realmente es lo que puedo hacer como ser humano, que es impulsarlos a los que me han pedido la ayuda, los que han pasado por mis salones de clase, pues simplemente he tratado de hacer lo que humanamente puedo para que sean mejores. Y creo que todos en gran medida se han convertido en mejores seres humanos, en mejores matemáticos. Y pues ver esos frutos realmente es muy reconfortante, ver estos muchachos y muchachas en distintas partes del mundo teniendo impacto y abriéndose su camino, pues es lo que uno como profesor, ese es el mejor pago para uno como profesor, que ver que los estudiantes, ¿cierto?, están respondiendo de manera muy positiva a ese hecho. En la Universidad del Valle tenemos una cosa especial, es que tenemos muchas mujeres haciendo matemática. Yo creo que es de los departamentos con más mujeres que hacen matemática, y eso realmente nos tiene muy felices. Muchísimas gracias, infinitas gracias a todos por las bellas palabras, por los gestos, a los invitados internacionales. Infinitas gracias. No pude estar en todas las conferencias, pero sí escuché muchas conferencias de un nivel pues espectacular y bueno, me siento pues muy agradecido y creo que ya tengo que jubilarme después de este homenaje, pues me toca vivir la jubilación ya. Les mando un abrazo de todo corazón y muchísimas gracias. Fueron muy generosos realmente. Y bueno, la Universidad del Valle es su casa y por acá lo estaremos esperando con los brazos abiertos. Me gustaría saber qué va a pasar con el Convimate, que es un evento que es de los eventos más importantes, me parece a mí, porque es un evento de los egresados que llegan aquí a Cali y que se reúnen a contar sus historias, a hablar de matemáticas. Espero que ese evento siga manteniéndose. Muchas gracias a todos.
Muchas gracias. Milton, ¿quisieras tomar fotos? Le pedimos a nuestros participantes que enciendan sus cámaras para que tomemos la tradicional foto. Jessica, ¿lo puedes anunciar tú?
Yeah, we are taking a picture. If you can turn on your camera, we will be grateful. And what? 3, 2, 1. Duan, ¿usted que está tomando la foto?
No, Milton, tómala tú, por favor.
Ah, Milton.
Tómala tú, por favor.
Milton is taking the photo.
Ok. 3, 2, 1.
Cheers.
Ok.
Thank you so much. Profesor Mario, usted dijo también algo muy bonito sobre el profesor Donaldson, si de pronto se lo puede decir en inglés, no sé si él entienda muy bien el español, para agradecerle también.
Probably Professor Donaldson speaks Spanish because his wife was professor at the Universidad del Valle also. And Anora Hurtado. Maybe he doesn't remember me, but I was in Universidad del Valle when you visited us in 1986, before you received the Fields Medal. I remember very well that you traveled at that time to California and came back to Cali with the medal. And also I attend your course at that time together with Jose Raul and also Gonzalo.
Oh.
I don't remember. At that time, Professor Carlos Rodriguez, he organized everything there. He is maybe our mentor in all these things. From this time, it's almost 40 years.
Yes.
Nice to see you again, Professor.
Very happy memories of both that visit in '86 and again in 2012. A short visit in 2012. But
yes, at that point, Brian was there. Was a student, and maybe Duvan. I don't know.
I hope we'll be able to visit again before long. Some point.
Yes. You are welcome every time, whenever you want to come.
O sea, podemos decir que hay como 3 generaciones, pues.
Claro.
En este momento, vean.
Yo diría que más. Gonzalo fue profesor de nosotros. Nosotros fuimos profesores de algunos de ustedes. Bueno, yo no tanto porque yo me fui un tiempo de la Universidad del Valle de Cali, de Colombia, y regresé hace poco a Colombia. Pero Raúl, que fue mi compañero de estudio.
Pero era para que el profesor Donaldson entendiera.
No, that's a good idea.
Es una broma, es una broma.
Thank you very
Está
much.
muy bien. Ok. Alexander Quintero, ¿quieres decir algo? Me pareció.
No exactamente, pero aprovecho la oportunidad para felicitar a Raúl por este merecido homenaje. Muchas felicitaciones, Raúl.
Muy bien.
Muchas gracias,
Bueno,
Alexander. Muchas gracias.
Ok, profesor Marley, entonces, ¿usted termina el evento con algunas palabras?
Ya
¿O ya
hablaba
lo...? Ok, muy bien. Bueno.
Usted que ha sido el cerebro detrás de todas estas actividades que se han hecho en los últimos años. Hace 2 años también estuve yo más involucrado que esta vez. Pero muchísimas gracias, de verdad, Juan. Gracias, Milton. Gracias, Jessica. Karina. Todos, de verdad. Brian. Mil gracias, porque de verdad el evento esta vez la sacaron del estadio, como decimos popularmente. Muchísimas gracias.
Profesor, listo. Entonces, muchas gracias a todos. Nos vemos en 2 años, quizá en una conferencia híbrida o en persona. Vamos a ver cómo ocurren las cosas. Bueno, chao.
Thank you so much to everyone. We hope to see you in 2 years. Okay. Hopefully we can maybe meet in person. So let's see what happens in the future. Thank you.
Bye.
Bye. Thank you.
Carolina.
Bye.
Bye. Thank you. Obrigado. Gracias.
Muito obrigado, Milton.
Muchas gracias. Felicidades.
Gracias a todos por participar.
Bueno.
Sí, muchas gracias y felicidades al profesor Raúl Quintero. Muy chévere el evento. Muchas gracias.
Muchas gracias, Alejandra. ¿Dónde estás?
Saludos, Raúl.
California.
En California, profe.
Ah, qué bueno.
¿Está frío ya, Alejandra?
Sí, bastante. Yo soy de calorcito. Me golpea.
Este año el invierno va a estar fuerte. La semana pasada cayó una nevada impresionante en Chicago. Va a estar
Bueno, aquí no hace
Llevamos una
nieve.
semana lloviendo todos los días, está lloviendo todos los días.
Allá no cae nieve, pero hace frío. Lloviendo ha estado todo el año, Raúl, yo creo. Es una cosa impresionante como ha llovido.
Todos los días. Y llueve bastante.
No, pues cerraron la carretera al mar, ¿no? La carretera Cali-Los Guerreros por eso.
Sí, hay un daño grave.
El río de agua se salió, eso estaba, mejor dicho. No sé, Gonzalo, si ha ido por allá.
Ok.
Bueno,
Bye
gracias
bye,
a
bye
todos.
bye, Ivane,
Gracias
bye
por la
bye, Milton, bye
organización.
bye, Jessica,
Bye.
bye bye, Tania, bye bye, Alejandra, bye bye,
Muchas gracias
Gonzalo.
por todo.
Chao, Alex.
Bye.
Chao, Gonzalo.
Ay, el profe Gonzalo.
¿Pero ya se fue?
Ahí
No,
está.
quedó como congelado él.
Bueno, chicos.
A ver, gracias, nos vemos.